You are listening to Arch Linux Administration Handbook, Building, Managing, and Securing Your System. Like and subscribe to keep up to date on our latest audiobooks. Arch Linux Administration Handbook, Building, Managing, and Securing Your System. Chapter 1, Understanding the Philosophy, Why Arch Linux, Introduction. In the vast and varied landscape of Linux distributions, Arch Linux stands out. It's often described with terms like minimalist, do-it-yourself, and bleeding edge. For anyone stepping into the realm of system administration, especially those who value deep understanding and absolute control over their environment, Arch Linux presents a compelling, albeit unique, proposition. Many find its initial reputation intimidating, associating it only with seasoned experts or command line gurus. But what if this perception misses the true essence of Arch? This book aims to demystify Arch Linux, transforming it from a hard distribution into a powerful tool for learning and mastering system administration. We'll explore not just how to administer an Arch system, but why its particular approach fosters a deeper understanding of Linux itself. This chapter lays the groundwork by diving into the core philosophies that define Arch, explaining its key features, and clarifying who stands to gain the most from its adoption. By the end, you'll have a clear picture of what makes Arch Linux tick and why it might be the perfect foundation for your journey into advanced Linux administration. 1.1 The Arch Linux Philosophy. KISS, DIY, and rolling release. At its heart, Arch Linux is guided by a set of principles that inform every aspect of its design and usage. Understanding these philosophies is crucial to appreciating the Arch way. KISS. Keep it simple, stupid. The KISS principle, applied to Arch Linux, doesn't mean it's easy to use in the sense of being user-friendly with graphical installers and pre-configured desktops. Instead, it refers to the simplicity of its design and structure. Arch eschews unnecessary complexity, layers of abstraction, and automatic configurations that obscure how the system works. For a system administrator, this translates to transparency. You can see exactly what's going on under the hood because there are fewer hidden scripts or automated processes. Control. Every component is installed and configured by the user, giving you unparalleled command over your system's setup. Minimalism. The base installation is incredibly lean, containing only the absolute essentials. You add only what you need, preventing bloat and improving performance. Imagine building a custom car. A simple design isn't one that drives itself, but one where every component is accessible, understandable, and intentionally placed, allowing you to easily maintain and tune it. That's the KISS principle in Arch. DIY, do-it-yourself. The do-it-yourself ethos is perhaps the most defining characteristic of Arch Linux. From the initial installation, which is performed manually via the command line, to the selection of your desktop environment, or lack thereof, Arch empowers the user to shape their system precisely to their needs. This DIY approach means no default desktop. Unlike many distributions that present you with a pre-selected desktop environment like GNOME or KDE, Arch provides only a command line interface post-installation. You choose and install your preferred graphical environment. Manual configuration. Most system configurations are done by editing text files, not through graphical wizards. This means understanding how configuration files relate to system behavior. Deep learning. By assembling your system piece by piece, you inevitably gain a deeper understanding of how Linux systems fundamentally operate, from bootloaders to network configurations. This hands-on learning is invaluable for any aspiring or experienced system administrator. Rolling release, always up to date. Unlike distributions that release major new versions every 6 months or 2 years, like Ubuntu or Fedora, Arch Linux operates on a rolling release model. This means continuous updates. There are no major version upgrades to worry about. Your system is always updated to the latest available software packages. When a new version of, say, Python or the Linux kernel is released, it typically lands in the Arch repositories very quickly. Fresh software. You always have access to the newest features, bug fixes, and security patches almost as soon as they are upstream. Streamlined maintenance. While regular updates are crucial, the process itself is generally simple. A single command keeps your entire system current. For example, you would frequently type something like sudo pacman-syu in your terminal to synchronize the package databases, and then upgrade all out-of-date packages. The potential downside, sometimes perceived as instability, is that very new software can introduce bugs. However, Arch's strong community and rigorous testing in the testing repositories generally mitigate major breakages. For a diligent administrator, the constant flow of updates becomes a feature, not a bug, offering consistent access to the latest tools and technologies. User-centric approach. At the core of these principles is the belief that the user knows best. Arch Linux doesn't make assumptions about your needs or preferences. It provides the tools and the freedom, allowing you to build a system that is perfectly tailored, efficient, and understood. 1.2 Key components and features. Beyond its philosophical underpinnings, Arch Linux relies on several key technological pillars that define its user experience and administrative workflow. Pacman, the Arch Package Manager. Pacman, short for Package Manager, is the heart of Arch Linux. It's a highly efficient and fast command line tool designed to manage all installed software packages. While other distributions use tools like apt from Debian/Ubuntu or DNF from Fedora RHEL, Pacman offers a unique blend of simplicity and power. Binary packages. Pacman deals primarily with precompiled binary packages, meaning software is ready to run once installed. Dependency resolution. It automatically handles dependencies, fetching and installing all necessary libraries and programs a given application needs to function. Repository management. Pacman interacts with Arch's official repositories, which are well-maintained and contain a vast array of software. Key operations. Basic commands involve synchronizing the package database, installing new packages, removing old ones, and upgrading the entire system. We'll delve into mastering Pacman in Chapter 3. Arch User Repository, AUR. Complementing Pacman and the official repositories is the Arch User Repository, or AUR. This is not an official repository, but a vast collection of recipes, called pkgbyld files, that allow users to compile and install software not available in the official repositories. Community maintained. The AUR is entirely community-driven. Users submit pkgbylds, and other users can vote on them, improving visibility and trust. Extensive software. If a Linux application in source form exists, there's a high chance you'll find a pkgbyld for it in the AUR. This includes niche tools, development versions, and proprietary software that cannot be redistributed directly. Building from source. When you install something from the AUR, you are typically downloading the source code and compiling it on your machine, or downloading a pre-built binary package provided by the developer. This process is managed semi-automatically by tools called AUR helpers, which we will discuss. Importance for sysadmins. The AUR is incredibly valuable for system administrators who often need specific versions of tools, less common utilities, or proprietary software that isn't open source enough for official distribution. The ArchWiki, unparalleled documentation. If Arch Linux has a secret weapon, it's the ArchWiki. This community-maintained online encyclopedia is widely regarded as one of the best, if not the best, Linux documentation resources available. Comprehensive. It covers virtually every aspect of Arch Linux, from installation steps to detailed configurations for specific applications, troubleshooting guides, and advanced topics. Up to date. Because of the rolling release model, the ArchWiki is continuously updated to reflect the latest changes and best practices. Accuracy. Its collaborative nature and a team of dedicated maintainers ensure high accuracy and quality. Your primary resource. For any Arch Linux administrator, the ArchWiki should be the first place you look when you have a question or encounter an issue. This book will guide you, but the wiki will be your ongoing companion. Systemed. The init system. Like most modern Linux distributions, Arch Linux uses Systemed as its init system. Systemed is responsible for booting your system, managing services, handling logging, and various other low-level tasks. Service management. Systemed provides a unified way to manage processes, ensuring applications start and stop correctly. For example, to start a web server service, you would typically use a command like sudo systemctl start apache.service. Journaled, its integrated logging system simplifies finding system messages. Instead of navigating separate log files, you can query the system journal. Central role. Understanding systems is fundamental to administering any modern Linux server or workstation, and Arch Linux makes its usage straightforward. We will dedicate an entire chapter, Chapter 4, to navigating systems. Minimal base system. When you first install Arch Linux, you're presented with a bare-bones command line environment. There's no default graphical interface, no pre-installed Office suite, and no media player. This is a deliberate choice. No bloat, you only install what you explicitly need. This results in a smaller disk footprint and fewer running services, which is beneficial for performance and security. Customization. You get to build your system from the ground up, choosing every component from your desktop environment, if any, to your preferred text editor and web browser. This level of customization allows you to create an incredibly efficient and personal computing environment. 1.3 Who is Arch Linux for, and who it isn't? Despite its reputation, Arch Linux is not exclusive to a mythical elite of superprogrammers. However, it's certainly not for everyone. Understanding its ideal user profile can help you determine if it aligns with your administrative goals. Ideal user, learners at heart. If you enjoy understanding how things work and are not afraid to get your hands dirty, Arch Linux is an unparalleled learning tool. It actively encourages you to explore and comprehend the underlying mechanisms of your operating system. Seasoned system administrators. Professionals who value fine-grained control, minimal overhead, and access to the latest software versions will find Arch Linux to be an incredibly powerful and flexible platform for servers, workstations, and development environments. Tinkerers and enthusiasts, those who enjoy customizing their systems, experimenting with new technologies, and maintaining control over every aspect of their software stack. Users comfortable with the command line. While graphical tools exist, the primary interaction with Arch, especially during installation and initial configuration, is through the terminal. A comfort level here is a big advantage. Less ideal user. Absolute beginners to Linux. If you're completely new to Linux and the command line, Arch's steep initial learning curve might be overwhelming. Distributions like Ubuntu or Mint offer a gentler introduction. Users who prefer it just works. If your priority is a system that comes fully pre-configured with a graphical interface and common applications right out of the box, Arch Linux requires a significant setup investment. Users with strict stability requirements for production systems without expertise. While a well-maintained Arch system can be very stable, the rolling release model means new software can occasionally introduce regressions. For mission-critical production systems, distributions with long-term support, LTS, releases, and more rigorous testing cycles, like Debian Stable or RHEL, might be preferred. Unless the administrator has the expertise and testing infrastructure to manage Arch's continuous updates. Anecdote: I remember my first attempt at Arch Linux years ago. Coming from Ubuntu, where everything was next, finish. The Arch installation guide felt like deciphering an ancient scroll. I failed, spectacularly, several times. But each failure forced me to look up commands, understand partitions, and grasp what a bootloader actually did. By the time I finally got a system up and running, I realized I had learned more about Linux fundamentals in one weekend than in months of using other distributions. It wasn't about the OS being hard, it was about it challenging me to learn. 1.4 The benefits for a system administrator. For a system administrator, the unique characteristics of Arch Linux translate into tangible benefits that can enhance skills and streamline operations. Deep understanding of Linux fundamentals. By forcing you to build your system, Arch ensures you understand the purpose of each component. File systems like etc. fstab, bootloaders, kernel modules, system services. This knowledge is transferable to any Linux distribution. You won't just know what command to type, you'll understand why you're typing it. Exceptional flexibility and control. Whether you're setting up a minimalist server, a powerful development workstation, or a specialized embedded system, Arch allows you to trim off all unnecessary fat and tailor the system precisely. This means more efficient resource usage and a system optimized for its specific task. Optimized performance. Because you only install what you need, an Arch system typically runs with less overhead, consuming fewer resources and often feeling snappier than distributions loaded with default services and applications you may never use. Access to latest software versions. In fast-moving IT environments, having access to the latest versions of libraries, compilers, databases, and other tools is crucial for developers and administrators. Arch's rolling release model ensures you're always up to date. This means faster access to new features, performance improvements, and critical security patches. Excellent documentation, ArchWiki. As mentioned, the ArchWiki is a goldmine. Its depth and accuracy mean that for most problems or configuration needs, a well-structured solution or explanation is often just a search away. This empowers administrators to self-sufficiently troubleshoot and configure complex setups. Strong community. The Arch Linux community is active and knowledgeable. While they encourage self-sufficiency, read the wiki first, the forums and other channels are vibrant with users willing to help and share knowledge. 1.5. Dispelling common myths and misconceptions. Let's address some of the widely held beliefs about Arch Linux that often deter potential users. Myth: Arch is hard to use. Reality: Arch Linux is not inherently hard. It is demanding of your knowledge. It assumes you are willing to learn and provides ample documentation to do so. The effort isn't in fighting complicated software. It's in understanding fundamental Linux concepts. Once you grasp these basics, the difficulty largely evaporates, replaced by logical steps. Myth: Arch is unstable or breaks easily. Reality: the rolling release model means you're always getting the newest packages, which can sometimes introduce bugs. However, Arch's packaging system and community testing typically catch severe issues. The perceived instability often comes from users who don't update regularly, don't read the news announcements before updating, or blindly install packages without understanding dependencies. A well-maintained Arch system, updated frequently and with attention to official announcements, is remarkably stable. It's stable because it's always current, fixing bugs quickly. The responsibility for stability largely rests with the administrator's diligence. Myth: Arch is only for experts. Reality: while many experts use Arch due to its flexibility, it is an excellent distribution for becoming an expert. Its DIY nature forces you to learn, making it a powerful educational tool for anyone serious about mastering Linux. Many users started with Arch as a relative beginner and grew their skills immensely through the experience. Conclusion: Arch Linux is more than just an operating system. It's a philosophy, a learning journey, and a powerful platform for system administration. Its commitment to simplicity in design, user control, and cutting-edge software provides an environment where you are constantly engaged, learning, and in command. It might demand more input from you initially, but it repays that investment with a profound understanding of Linux and unparalleled flexibility. This chapter has set the stage by detailing the core tenets of Arch Linux. In the next chapter, we'll roll up our sleeves and embark on the most fundamental step of any Arch journey: the installation. This hands-on experience will immediately put the philosophies of KISS and DIY into practice, setting you on the path to becoming a proficient Arch Linux administrator. Chapter 2: The Arch Installation Journey, Building from the Ground Up. Introduction. In the previous chapter, we delved into the philosophical underpinnings of Arch Linux, exploring its commitment to simplicity, user control, and staying current with the latest software. Now it's time to put those principles into practice. The installation of Arch Linux is perhaps the most defining, do-it-yourself experience you'll have with this distribution. Unlike many other Linux systems that offer graphical installers and automated setup routines, Arch requires a hands-on, command line approach from start to finish. This journey is not just about installing an operating system. It's a foundational learning experience. By manually configuring each component, you gain an intimate understanding of how a Linux system is built from the ground up. This knowledge is invaluable, offering insights that are transferable to any Linux distribution you might encounter in your system administration career. This chapter will guide you step by step through the process of installing a basic, functional Arch Linux system. We'll cover everything from preparing your installation media to configuring the bootloader. While we will mention commands and their typical usage, the focus will be on explaining what you're doing and why, rather than providing literal code blocks, making it accessible for both reading and listening. 2.1 Preparing for installation, the pre-flight checklist. Before we begin the actual installation, a little preparation goes a long way. Think of this as your pre-flight checklist, ensuring you have all the necessary components and information ready. Downloading the Arch Linux ISO. Your journey begins with the Arch Linux installation image, known as an ISO file. You should always download this from the official Arch Linux website, archlinux.org. Navigate to the Download section, where you'll find links to various mirrors. It's always a good practice to verify the integrity of your download by checking its checksum. This ensures that the file hasn't been corrupted during download and hasn't been tampered with. The website typically provides SHA-256 sums for this purpose. You would use a command line utility on your current operating system, such as SHA-256 sum, to compare the value generated from your downloaded ISO with the value published on the Arch Linux website. Creating bootable media. Once downloaded, the ISO needs to be written to a bootable medium, typically a USB flash drive. This will transform your USB drive into a mini Arch Linux live environment that you can boot your computer from. For this task, you have several options. Etcher, Balna Etcher. This is a popular graphical tool available for Windows, Mac OS, and Linux. It's user-friendly and reliable for burning ISOs to USB drives. You would simply select your downloaded ISO, choose your USB drive, and begin the process. The DD command. For Linux or Mac OS users comfortable with the command line, the DD utility is a powerful and direct way to write the ISO. You would type a command similar to sudo dd if /path/ to / your / arch linux size of /dev/ sdxbs equals 4m status equals progress, replacing path/ to / your / arch linux size with the actual location of your ISO file and /dev/ sdx. With the device name of your USB drive, be extremely careful here, as writing to the wrong device can erase data. The BS equals 4m part optimizes the block size for faster writing, and status equals progress gives you a visual update. Ensure your USB drive has at least 2 GB of storage capacity. Internet connection. A wired Ethernet connection is highly recommended for your first Arch Linux installation. The installer will need to download packages from the internet, and a stable, fast connection simplifies this process immensely. While wireless connectivity is possible, it adds an extra layer of configuration that can be challenging if you're new to the command line. Hardware knowledge. Before booting, familiarize yourself with your computer's basic hardware settings. You'll need to access your system's UEFI or BIOS settings to ensure it boots from your newly created USB drive. You may also need to disable Secure Boot if it's enabled and you're installing on a UEFI system, as it can sometimes prevent Linux distributions from booting. Knowing how to access your machine's boot menu, often by pressing F2, F10, F12, or delete during startup, is crucial. Dual booting considerations. If you plan to install Arch Linux alongside an existing operating system, like Windows or another Linux distribution, remember to back up any important data from your existing operating system. While the process is generally safe, accidents can happen. Free up unallocated space on your hard drive before you begin. You can usually do this from within your existing operating system's disk management tools. Be prepared for potentially complex bootloader configurations, especially with Windows. Essential cheat sheet. Keep notes. Have a second device, like a smartphone or another computer, handy that can access the Arch Wiki. This will be your lifeline for looking up details or troubleshooting. 2.2 Booting into the live environment. With your bootable USB ready, insert it into your computer and restart. You'll need to either physically change the boot order in your BIOS UEFI settings or select the USB drive from your system's one-time boot menu. BIOS UEFI settings. Navigate your computer's Setup menu. If you have a modern system, ensure UEFI mode is enabled and Secure Boot is disabled. Legacy BIOS systems will simply boot. Arch Linux boot menu and welcome to the TTY. After selecting your USB drive, you'll be greeted by the Arch Linux boot menu. Choose the Arch Linux Install Medium option. After a few moments, your screen will transition to a black background with white text, culminating in a command line prompt. This is your terminal, your primary interface for the installation process. You are logged in as the root user, which has full system privileges. Keyboard layout. The default keyboard layout is US English. If you use a different layout, you'll want to change it immediately. You can list available key maps by typing ls/share/kbd/keymaps/your-layout-map-gz. For example, to find German layouts, type ls/share/kbd/keymaps/mapgz grepta. Once you know your layout, you would type a command such as loadkeys d Latin 1 to set a German keyboard layout. Verify boot mode. It's important to know whether your system booted in UEFI or BIOS, legacy, mode, as this affects how you configure your partitions and bootloader. To check for UEFI mode, type lsys/firmware/efi/f. If this command returns a directory listing without errors, you are in UEFI mode. If it returns an error, you are likely in BIOS mode. Network configuration. Wired connection. If you're using a wired Ethernet connection, it's usually configured automatically via DHCP. You can verify your connection by typing IP-ALOOK for an Ethernet interface, often named EMP-XSY or ETH0, with an IP address assigned. You can also test connectivity by pinging a well-known website, like typing pingarchlinux.org. Wireless connection, if necessary. If you must use Wi-Fi, the Arch Linux Live environment uses the ILCTL utility. The general steps involve listing Wi-Fi devices, ILCTL device list, scanning for networks, ILCTL station Wi-Fi 0 scan, replace Wi-Fi 0 with your Wi-Fi device name, listing available networks, ILCTL station Wi-Fi 0 get networks, connecting, ILCTL station Wi-Fi 0 connect, your SSID name. You will then be prompted for your Wi-Fi password. Confirm connectivity again with pingarchlinux.org. Update system clock. Ensure your system's clock is accurate. This is important for proper system operation and secure connections. Set it by typing timedate setntp true. This command enables Network Time Protocol, NTP, synchronization, which automatically keeps your clock accurate using Internet time servers. Check Pacman mirrors. Pacman, Arch's package manager, downloads software from mirrors servers that host the Arch Linux repositories. The installer automatically ranks these mirrors. To ensure you have an up-to-date list and potentially faster downloads, it's good practice to force a full refresh of the package databases by typing pacman-c. You may also wish to edit the mirror list at /etc/pacman-d/mirrorlist to place faster, geographically closer mirrors at the top. The Rank Mirrors utility can assist with this, but for a first install, ensuring you have internet access and the base mirrors are working is sufficient. 2.3 Partitioning the disks. Laying the foundation. This is a critical step where you define how your hard drive space will be allocated for your Arch Linux installation. Understanding disk layout. Your storage drives are typically named using a specific pattern. Solid-state drives, SSDs, connected via NVMe often appear as dev/NVMe 0 and 1, while SATA SSDs or traditional hard drives are usually /dev/SDA, /dev/SDB, and so on. Partitions on these drives are then numbered. For example, /dev/SDA1, /dev/SDA2. Tools for partitioning. Several command line tools can partition your disk. fdisk, a classic text-based tool suitable for both MBR master boot record and GPT GUID partition table partitioning, though gdisk is often preferred for GPT. gdisk, a GPT-aware partitioning tool, highly recommended for UEFI systems. Parted, a more modern and powerful partitioning tool that can perform operations on the fly, but generally fdisk or gdisk are simpler for initial setup. For this guide, we'll conceptually walk through fdisk or gdisk if you prefer for UEFI for setting up a straightforward partitioning scheme. Recommended partition scheme, simple. For a basic system, we will create 2 to 3 partitions. EFI system partition, ESP. Required for UEFI systems. This is a small partition, typically 512 megabytes to 1 gigabyte, formatted as FAT32. It stores the bootloader and related files. It will be mounted at boot/EFI. If you are in BIOS legacy mode, you do not need an ESP. Root partition. This is where your entire Arch Linux system, except perhaps your user data, will reside. It should be formatted with the ext4 file system, which is common and robust. It should take up the bulk of your chosen disk space. This partition will be mounted at /mnt. Swap partition, optional but recommended. A swap partition acts as virtual memory. When your system runs out of physical RAM, it can use this space on the hard drive. Its size depends on your RAM and workload, often matching or being twice your RAM size, but never more than 16 gigabytes. It doesn't get mounted in the traditional sense, but is enabled as swap space. Alternatively, you can use a swap file, a file on your root partition, after installation. Conceptual demonstration with fdisk or gdisk. First, identify your target disk using lsblk. For example, let's assume your disk is /dev/sda. You would type fdisk dev/sda. The utility will start. If you are on a UEFI system, you'll want a GPT partition table. Type G to create a new empty GPT partition table. To create a new partition, you would type N. You'll be prompted for the partition number, first sector, and last sector, or size. For the EFI system partition, you'd typically allocate 512 megabytes. Then you type T to change the partition type, selecting the appropriate code for EFI system, usually 1 if using fdisk or EF00 for gdisk. For the root partition, you'd create another new partition, N, allowing it to take up the majority of the remaining space. You'd typically let it default to Linux file system type. For the swap partition, if you choose to create one, create a small partition and then change its type to Linux swap. Finally, to write your changes to the disk, you would type W. The utility will then exit. Warning: this process will erase all data on the partitions you create and format. Double-check your disk selection. Formatting partitions. After partitioning, you need to format each partition with its intended file system. EFI system partition. Use mkfsfat-f32 dev/sda1, assuming sda1 is your ESP. Root partition. Use mkfsext4 dev/sda2, assuming sda2 is your root. Swap partition. Use mkswap/dev/sda3, assuming sda3 is your swap, and then enable it with swap-on/dev/sda3. 2.4. Mounting the file systems. Now that your partitions are ready and formatted, you need to mount them, making them accessible to the Arch Linux installer. Create a mount point for the root partition. Type mkdir/mnt. Mount the root partition. Type mount/dev/sda2/mnt using your root partition's device name. Create mount points for other partitions. If you have an EFI system partition, you'll need to create its mount point within the root mount point. mkdir p/mnt/boot/EFI. Mount the EFI system partition. Type mount dev/sda1/mnt/boot/EFI. If you chose a separate home partition, you would also create mkdir/mnt/home and then mount/dev/sdb1/mnt/home, for example. Verify mounting. You can check if your partitions are correctly mounted by typing lsblkf. This command shows disk devices and their mount points, confirming your setup before proceeding. 2.5. Installing the base system. With your partitions prepared and mounted, you can now install the core Arch Linux system onto your new root partition. The power of Packstrap. The Packstrap utility is specifically designed for installing the essential packages onto a newly mounted system. You would type a command such as packstrap/mnt base Linux firmware. Let's break down what these packages provide. Base. This is the meta package that includes the essential tools and utilities required for a minimal Arch Linux installation, like the bash shell, common file utilities, and basic system configuration tools. Linux, this is the official Linux kernel package. It's the core of your operating system. Linux firmware. This package contains the necessary firmware files for various hardware components, e.g., Wi-Fi adapters, graphics cards, to function correctly with the kernel. Optional but recommended packages for convenience. You might also consider adding basedevel, essential for building packages, especially from the AUR later, and Network Manager, a robust tool for managing network connections, which you'll configure later to this packstrap command. So your command might look like packstrap/mnt base Linux firmware basedevel network manager. The installation process will begin downloading the selected packages from the internet and installing them onto /mnt. This may take some time depending on your internet speed. The system will display progress updates as packages are fetched and extracted. 2.6 Basic System Configuration. After installing the base system, you need to perform some fundamental configurations to make it bootable and usable. You'll do this from within the context of your newly installed system using the archroot command. fstab generation. The fstab file, /etc/fstab, tells your Linux system which disk partitions to mount at boot time and where to mount them. It's crucial for your system to start correctly. Generate this file automatically by typing gemstab u/mnt/etc/fstab. The U option uses UUIDs, universally unique identifiers, for partitions, which is more reliable than device names. The redirects the output of gemstab to append it to the fstab file within your new system. Crooting into new system. Now you'll croot into your newly installed Arch Linux environment. This command changes your effective root directory from the live USB environment to the root of your newly installed system. You'll be working directly on your new Arch installation from this point forward. Type archroot/mnt. Your command prompt might change, indicating you are now operating within the crooted environment. Time zone. Set your time zone and synchronize the hardware clock. Symlink your desired time zone file. Type ln sf/share/zoneinfo/region/city etc/local time. For example, for New York, you would type ln sf/share/zoneinfo/america/New York etc/local time. Set the hardware clock from the system time, HW clock systoc. Localization, localgen, local.conf. Localization defines the language and locale settings for your system. Edit the localgen file. Open it using a simple text editor like Nano. Type nano etc localgen. Find the line corresponding to NUSUTF-8 UTF-8 or your preferred locale and uncomment it by removing the hash symbol at the beginning of the line. Save and exit Ctrl+O, enter Ctrl+X in Nano. Generate the locales, type localgen. Set the default system language. Type echo lang equals NUSUTF-8 etc locale.conf. Network configuration. Persist after reboot. You need to ensure your network connection works after you reboot into your new system. If you did not install Network Manager with Packstrap, install it now. Pacman S Network Manager. Enable the Network Manager service so it starts automatically at boot. Systemtl enable Network Manager. Set your system's hostname, the name your computer will be known by on the network. Type echo myarch etc/hostname, replacing myarch with your desired hostname. Edit the hosts file etc hosts to map hostnames to IP addresses. Open the file with nano etc hosts and add the following lines. 127.0.0.1 localhost. 1 localhost. 127.0.1.1 myarch local domain myarch. Again, replace myarch with your chosen hostname. Root password. It's critical to set a password for the root user. This is the superuser account, and it should always be secured. Type password. You will be prompted to enter a new password twice. User account, crucial for daily use. Running as root for daily tasks is a serious security risk. You should always create a regular user account. Add a new user. Type useradd m, g users gwheel power, audio, Video sbin bash username, replacing username with your desired username. M. Creates a home directory for the user. G. Users. Assigns the user to the user's primary group. G. Wheel, power, audio, video. Adds the user to additional groups that provide permissions for common tasks, e.g., wheel for pseudo access, power for shutdown, audio and video for multimedia. Sbin bash sets the default shell to bash. Set a password for the new user, type password username. You'll be prompted to enter the password twice. Enable sudo for your new user. To allow your user account to execute commands with root privileges, using the sudo command, you need to configure the sudoers file. This is best done with the vsudo command, which provides syntax checking. Type editor equals nano vsudo. This opens the sudoers file in the nano editor. Find the line that looks like #%wheel all equals all, and uncomment it by removing the leading hash symbol. This line allows any user in the wheel group to use sudo. Save and exit. 2.7 Installing a bootloader. Your system now has a kernel and essential files, but it needs a bootloader to actually start up the Arch Linux operating system when you power on your computer. Grub Grand Unified Bootloader is a very common and versatile choice. Grub for UEFI systems. If you installed Arch Linux in UEFI mode, follow these steps. Install grub and fbootinger. Type Pacman s grub fbootinger. Fbootinger is a utility for managing UEFI boot entries. Install grub to your EFI system partition. Type grub install target equals x8660 for EFI directory equals /boot /EFI bootloader ID equals grub. This command places the necessary grub files into your EFI system partition and registers grub with your system's UEFI firmware. Generate the grub configuration file. Type grub mkconfig o/boot/grub/grubcfg. This command scans your system for operating systems, including Arch Linux itself, and creates the configuration file that grub uses to present boot options. Grub for BIOS systems. If you installed Arch Linux in BIOS legacy mode, the steps are slightly different as there is no EFI system partition. Install grub. Type Pacman s grub. Install grub to the master boot record, MBR, of your disk. Type grub install dev/sda. Replace dev/sda with your primary disk device, not a partition. Generate the grub configuration file. Type grub mkconfig o/boot/grub/grubcfg. 2.8 Final steps and first boot. You're almost there. Just a few more steps before you can reboot into your brand new Arch Linux system. Exit Croot. You are still in the crooted environment. To exit back to the live USB environment, simply type exit. Unmount partitions. It's good practice to unmount all mounted partitions before rebooting. Type umount r/mnt. The R option ensures that all subdirectories and mounted file systems under /mnt are unmounted. Reboot. Remove your USB installation medium from the computer, then type reboot. Your computer should now restart, and if all went well, you'll be greeted by the grub boot menu, quickly followed by the Arch Linux console login prompt. If you see text scrolling rapidly and then a login prompt, congratulations. You have successfully installed Arch Linux. Log in with the regular user account you created, not the root user, and enter your password. You are now running on your newly installed Arch Linux system. Conclusion. You've just completed the foundational step of building an Arch Linux system from scratch. This intensive journey from a command line prompt on a live USB to a fully functional base system has put the do-it-yourself philosophy into action. You've partitioned disks, formatted file systems, installed the core operating system, and configured essential services, gaining a deep, tangible understanding of system initialization and structure. While your Arch Linux system is now operational, it's currently a bare-bones command line environment. In the next chapter, we'll dive into mastering Pacman and the Arch user repository, crucial tools that will allow you to expand your system, install new software, and manage your Arch Linux environment effectively. Chapter 3, Mastering Pacman and the AUR, the Arch Package Ecosystem. Introduction. In the previous chapter, you embarked on a hands-on journey, building your Arch Linux system from the ground up, configuring its fundamental components, and installing the essential base operating system. You now have a lean, powerful command line environment ready for anything. But what next? A core system, by definition, is minimal. To transform it into a truly usable workstation or server, you'll need applications, utilities, and additional software. This is where Arch Linux's unique package management ecosystem comes into play. At its heart lies Pacman, the official package manager, an incredibly fast and efficient tool for handling software from Arch's official repositories. Complementing Pacman is the Arch User Repository, or AUR, a remarkable community-driven collection that significantly expands the range of available software. Together, Pacman and the AUR form a robust and flexible system for managing virtually any software you might need. Understanding and mastering these tools is paramount for any Arch Linux administrator. They embody Arch's philosophy of user control and direct access to software. This chapter will guide you through the intricacies of Pacman for official packages, and then introduce you to the vast world of the AUR, explaining how to leverage both safely and effectively. 3.1 Pacman, the core package manager. Pacman, short for package manager, is the native package manager for Arch Linux. Written in C, it's renowned for its speed, simplicity, and robustness. Pacman manages official binary packages from the Arch Linux repositories, handling everything from installation and removal to system updates and dependency resolution. What Pacman does: synchronize databases. It downloads the latest information about available packages from the Arch Linux servers. Install packages. It fetches requested software packages and their dependencies, then installs them onto your system. Remove packages. It cleanly uninstalls software, with options to remove dependencies that are no longer needed. Upgrade the system. It keeps your entire Arch Linux installation up to date by upgrading all installed packages to their latest versions. Query information. It allows you to search for packages, list installed files, and check package information. Basic Pacman syntax and operations. Pacman commands generally follow a Pacman -option package name structure. Here are the most common operations you'll use daily. Synchronize and update your system. CU. This is arguably the most important Pacman command. You should run it regularly, often before installing new software, to keep your system current. You would type sudo pacman cu. Sudo executes the command with superuser privileges, which is required for package management. S stands for sync. It synchronizes package databases. Y refreshes all package databases. This downloads the latest list of packages and their versions from the Arch mirrors. U upgrades all installed packages to their newer versions based on the refreshed databases. When you run this command, you'll first see Pacman downloading database files. Then it will check for new versions of packages on your system, list them, and ask for confirmation before downloading and installing the updates. Install a new package, S. To install a new piece of software, you use the sync option followed by the package name. For example, to install the htop utility, which shows you the running processes, sudo pacman htop. Pacman will automatically download htop and any other packages it depends on that are not already present on your system. It will show you a list of packages to be installed and ask for confirmation. Remove a package rs, rns, to remove a package without touching its dependencies. Sudo pacman r package name. To remove a package and any dependencies that are no longer required by other installed packages. Sudo pacman rs package name. This is typically the recommended way to remove software, as it helps keep your system clean. To remove a package, its unneeded dependencies, and its configuration files. Sudo pacman rns package name. Use this when you want a complete removal, as if the package was never there. Search for packages, ss, qs, ql, to search for packages in the official repositories, the sync databases. Pacman ss keyword. For example, to find packages related to editor, Pacman ss editor. This will list packages whose names or descriptions contain the keyword. To search for packages already installed on your system, Pacman qs keyword. To list all files owned by an installed package, Pacman ql package name. This is useful for understanding where a program's executables, libraries, and configuration files are located. Query package information to view detailed information about an installed package. Pacman package name. This shows the version, dependencies, installation date, and other metadata. To show even more verbose information about an installed package, including backup files. Pacman package name. Clean the Pacman cache, SCC. Pacman stores downloaded package files in a cache, typically in the /var/cache/pacman/pkg/ directory. This allows you to reinstall or downgrade packages without re-downloading them. To remove old, uninstalled package versions from the cache while keeping the latest installed versions. Sudo pacman sc. To clear all packages from the cache, including currently installed ones, sudo pacman scc. Use scc with caution, as it makes downgrading or offline reinstallation impossible without re-downloading. 3.2. Pacman configuration and best practices. While Pacman is intuitive, a few configuration details and best practices can enhance your administrative workflow. Mirror selection. Pacman relies on mirrors, which are servers around the world that host the Arch Linux package repositories. The speed and reliability of your updates depend heavily on which mirrors your system uses. Location. The list of mirrors your system uses is in the file etc/pacmand/mirrorlist. Editing. You can edit this file manually using a text editor like nano. Sudo nano etc/pacmand/mirrorlist. You'll see a long list of mirror URLs, often commented out with a hash symbol. Uncomment. Remove the mirrors that are geographically closest to you, and place them at the top of the list. Pacman uses mirrors in the order they appear. Automated ranking. For more advanced users, tools like Reflector can automate this process. You can install Reflector with sudo pacman sreflector and then run it with sudo reflector country, US, age 24 protocol HTTPS sort rate save /etc/pacmand/mirrorlist. This command, for example, fetches HTTPS mirrors from the United States that have been updated within the last 24 hours, sorts them by download rate, and saves the new list to your mirror list file. This ensures you always have the fastest, most up-to-date mirrors. Pacman hooks. Pacman uses hooks, which are scripts that automatically run before or after certain package operations, like installation, upgrade, or removal. You'll typically find these in usr/share/libulpum/hooks/. For instance, a hook might automatically regenerate your kernel images after a kernel upgrade, or update a systemed service configuration. These generally work in the background, but understanding their existence can be helpful for troubleshooting unexpected system behavior after updates. Security. Package signature checking. By default, Pacman rigorously checks the cryptographic signatures of all packages it downloads. This ensures that the packages haven't been tampered with and truly originate from the Arch Linux developers. You'll see this configuration in /etc/pacman.conf under the Options section, typically sig level equals required database optional. This is a crucial security feature that helps maintain the integrity of your system. Updating best practices. Always update first. Before installing any new software, always run sudo pacman su. This ensures your package databases are up to date, preventing potential dependency conflicts that could arise from installing a new package against outdated local information. Don't partially update. Avoid situations where you only synchronize databases, pacman su, but don't upgrade pacman su before installing a specific package, pacman s package name. This can lead to a partial update scenario where core system libraries might be outdated while a new application expects newer versions, potentially causing instability. Always do a full CU. Read the news. Before performing a significant system update, especially after a period of not updating, it's highly advisable to check the official Arch Linux news on the Arch Linux website or forum. Developers occasionally post important information about required manual intervention for certain updates, or warnings about changes that might affect your system. Log files. Pacman keeps a detailed log of all transactions in /var/log/pacmanlog. This file is invaluable for troubleshooting. If your system behaves unexpectedly after an update, Reviewing this log can often provide clues about what changed. Anecdote: I once had a user on a non-Arch system complain that their application suddenly stopped working after they tried to install something new. After some digging, it turned out they had manually installed a package from a third-party source that conflicted with core system libraries, overriding newer versions with older ones. On Arch, Pacman's strict dependency management and its best practices, like discouraging partial updates, are designed to prevent such common pitfalls. It empowers you by making you explicitly aware of dependencies and changes. 3.3 The Arch User Repository, AUR. Community power. While Pacman handles the official packages, the strength of the Arch Linux ecosystem extends far beyond. The Arch User Repository, AUR, is a vast community-driven resource that contains thousands of user-submitted recipes for building software. If a Linux application is not in the official repositories, there's a very good chance you'll find it in the AUR. What is the AUR? The AUR is not a repository of pre-built binary packages like the official Arch repositories. Instead, it hosts pkgbuild scripts. A pkgbuild is a shell script that contains instructions on how to download the source code for a piece of software, compile it, and package it into a format that Pacman can install. Community maintained, users submit PKG builds. Other users can vote on them, comment, and sometimes take over maintenance. Expansive software selection. The AUR is a treasure trove for niche software, development versions of popular applications, proprietary software, where the developer only provides binaries and not source code, and anything else that might not meet the strict criteria for inclusion in the official repositories. Crucial for sysadmins. For system administrators, the AUR is invaluable. It provides access to a wide array of specialized tools, monitoring agents, less common scripting languages, and specific versions of software sometimes required for compatibility. The AUR process, manual building for understanding. Before using helper tools, understanding the manual process of building from the AUR is crucial for safety and education. Find the package. Browse the AUR website or .archlinux.org and search for the software you need. Each package has its own page. Clone the repository. Each AUR package has a Git repository associated with it. You would clone this repository to your local machine, typically into a temporary directory in your home folder. For example, for a hypothetical example app package, git clone https or .archlinux.org/example-appgit. Enter the directory, change into the newly cloned directory, cd example app. Examine the pkgbuild. This is the most critical step. Open the pkgbuild file with a text editor, nano pkgbuild, and carefully read its contents. It lists the source URL, dependencies, and all steps involved in building and packaging the software. This is where you check for any potentially malicious code or unexpected instructions. Build and install. Once you've reviewed the pkgbuild and are satisfied, you use the makepkg utility to build the package. Run. Makepkg. Makepkg. This command interprets the pkgbuild and orchestrates the download, compilation, and packaging. S. Resolves and installs any dependencies required at build time that are available in the official repositories. I. Installs the newly built package onto your system using Pacman. This command will often take some time as it downloads source code, compiles it, which can be CPU intensive, and then produces a pkg-tarzsd file that Pacman can install. Security considerations for AUR. This manual process highlights a crucial point. AUR packages are user-submitted and not officially vetted for security by Arch Linux developers before being made available. While the community generally self-polices, you are responsible for reviewing the pkgbuild script before building. Always review. Never, ever, blindly run makepkg on an AUR package without first inspecting its pkgbuild file. Look for unusual source URLs, unexpected commands, or anything that seems out of place. Do not build as root. Always run makepkg as a regular user, not as the root user. This limits the potential damage if a malicious pkgbuild were to execute commands during the build process. Only the final Pacman U install file step requires sudo privileges, and by then, the package has been built and verified. Community queues. Pay attention to comments, votes, and out-of-date flags on the AUR website. A highly voted, well-maintained package with positive comments is generally safer, but not infallible. 3.4. Streamlining with AUR helpers. The manual process of cloning, reviewing, building, and installing AUR packages can be tedious, especially when dealing with many packages or frequent updates. This is where AUR helpers come in. What are AUR helpers? AUR helpers are command line utilities that automate the process of interacting with the AUR. They largely mimic Pacman's syntax and integrate seamlessly with it, making the management of both official and AUR packages feel like a single, unified process. They handle the cloning, dependency resolution, PKG-BUILD review by displaying it, building, and installation for you. Popular examples. The most popular and well-regarded AUR helpers include Yay and Paru. Both are written in Rust, fast, and feature-rich. Installation. AUR helpers themselves are typically found in the AUR, so you would need to install your first AUR helper manually using the makepkgc process described above. For Yay, you would clone its Git repository and build it. Common AUR helper operations, using Yay as an example. Once Yay, or your chosen helper, is installed, your package management workflow simplifies dramatically. Sync and update all packages, official and AUR. This is one of the most powerful features. A single command updates everything on your system. Yay or Yaysu. The helper first calls Pacman to update official packages, then checks for updates to your installed AUR packages, rebuilding them if new PKG-BUILDs are available. You will be prompted to review any PKG-BUILD changes for AUR packages. Install an AUR package, Yay-S package name. For example, to install the Visual Studio Codebin package from the AUR, Yay-S Visual Studio Codebin. The helper will fetch the PKG-BUILD, resolve dependencies, official ones via Pacman, AUR ones via the helper itself. Display the PKG-BUILD for your review, and then build and install the package. Search for an AUR package, Yay-SS keyword. This will search both official repositories and the AUR. Important considerations for AUR helpers. Still your responsibility. While AUR helpers simplify the process, they do not absolve you of the responsibility to review PKG builds. Most helpers will offer to display the PKG-BUILD and its diff changes since last build, and you should always take advantage of this. Don't blindly press yes to every prompt. Convenience, not safety net. AUR helpers are convenience tools. They do not magically make unverified AUR packages safe. Your diligence in reviewing is the primary security measure. Choosing an AUR helper. Both Yay and Paru are excellent choices. They are actively maintained, widely used, and offer very similar functionality and syntax. Many users choose based on personal preference or familiarity. Conclusion. Mastering Pacman and the Arch user repository is fundamental to effective Arch Linux system administration. Pacman provides a clean, fast, and robust mechanism for managing software from the official repositories, underpinning the stability and currency of your system. The AUR, with its vast community-driven collection of software, extends Arch's versatility dramatically, making it possible to install virtually any Linux application. By understanding how these tools work, adhering to best practices, especially regarding updates and PKG-BUILD review, and leveraging AUR helpers intelligently, you gain unparalleled control over your software environment. This deep control is a hallmark of the Arch Linux experience and a powerful advantage for any system administrator. With your system now capable of installing and managing software, our next step is to understand how Arch Linux manages its processes and services. In Chapter 4, we will dive into Systemd, exploring its role in booting, service management, and logging, equipping you with the knowledge to control your Arch system's background operations. Chapter 4, Navigating Systemd, Services, Units, and the Journal. Introduction. In the journey of mastering Arch Linux, you've successfully built your base system and gained proficiency in managing software packages with Pacman and the AUR. Your system now lives as a robust, minimalist foundation. But a computer system is more than just installed programs. It's a dynamic environment where numerous processes run continuously in the background, managing everything from network connections to scheduled tasks. These background processes, often called daemons or services, are the unsung heroes that keep your system functioning. This is where Systemed comes in. Systemed is the modern init system and service manager that has become a fundamental component of most contemporary Linux distributions, including Arch Linux. As an administrator, understanding Systemed is absolutely vital. It provides a unified, structured, and powerful way to control nearly every aspect of your system's boot process, service lifecycle, and logging. In this chapter, we will demystify Systemed. We'll explore its core concepts, learn how to manage services with the systemctl command, understand the role of different unit types, and delve into journoctl, Systemed's integrated logging utility. By the end, you'll be equipped with the knowledge to effectively manage the beating heart of your Arch Linux system. 4.1 What is Systemed? The modern init system. At its simplest, an init system is the very first process that the Linux kernel starts. This process, traditionally called init, short for initialization, then takes responsibility for starting all other processes, services, and handling various bootup sequences. It's the parent of all other processes on your system. Historically, Linux distributions used simpler init systems like sysvinit, system5 init. These were often sequential, meaning services started one after another, which could be slow. Systemed was designed to address many of the limitations of these older systems. Key characteristics and advantages of Systemed. Parallelization. Systemed can start many services simultaneously, leading to significantly faster boot times compared to older, sequential init systems. Unified control. It provides a consistent framework for managing a wide range of system resources, not just services. On-demand activation. Services can be started only when they are needed, rather than running all the time, saving resources. For example, a print server might only start when a print job is initiated. Robust dependency management. Systemed understands complex relationships between services, ensuring that dependent services start in the correct order. Centralized logging. It integrates a powerful logging system called Journaled, which collects and manages all system and application logs in a structured way. API for services. Systemed exposes an application programming interface, or API, that services can use to communicate with it, allowing for more intelligent process management. Systemed goes beyond simply starting and stopping services. It is an entire suite of management daemons, libraries, and utilities that manage many aspects of the system, including network configuration, device management, user sessions, and hardware events. 4.2 Systemed units. The building blocks. The core concept in Systemed is the unit. Every resource that Systemed manages is represented by a unit file, which is a plain text configuration file describing that resource. These files usually end with a suffix that indicates the unit type. Common unit types you'll encounter. Service units. These are the most common and represent background processes, or daemons. Examples include web servers, database servers, and network services. Target units. These act as synchronization points or groups of other units. They represent specific system states or milestones, similar to run levels in older init systems. For example, multi-user target represents a fully functional text-based system with networking, while graphical target includes a graphical user interface. Mount units. These define file system mount points, specifying which partitions should be mounted where. Socket units. These listen on network or interprocess communication sockets. They allow services to be activated on demand when a connection request arrives. Device units. These represent kernel devices, allowing system to manage hardware events. Dot timer units. These are used for scheduling tasks, similar to how cron jobs work. A timer unit can trigger a service unit at specific times or intervals, where unit files reside. Systemed unit files are typically located in several directories, with a clear hierarchy that defines precedence. Usr/lib/systemd/system/. This is where unit files supplied by installed packages, official packages, are stored. You should never edit files in this directory directly, as your changes would be overwritten during package updates, etc. System. This directory is for system administrators to place their own custom unit files or override default settings from /usr/lib/systemd/system/. Any file here takes precedence over a file with the same name in usr/lib/systemd/system/. You would create new unit files here, or create a subdirectory, e.g. service name service D, to place drop-in conf files for specific overrides without copying the entire unit file. Understanding this hierarchy is important to manage your system effectively and prevent unexpected behavior after system updates. 4.3. Managing services with systemtool. The primary command line utility for interacting with systemd is systemtool. It's your everyday tool for starting, stopping, enabling, disabling, and checking the status of services and other units. Here are the most common systemtool commands you'll use. Starting a service. To manually start a service, like an Apache web server, sudo systemtool start Apache service. The service extension is often optional if the context is clear, so sudo systemtool start Apache would also work. Stopping a service. To stop a running service, sudo systemtool stop Apache service. Enabling a service, auto start at boot. To configure a service to start automatically every time your system boots up, you enable it. Sudo systemtool enable Apache service. Behind the scenes, this typically creates a symbolic link from the unit file in usr/lib/systemd/system, or etc. system, to a subdirectory within etc. system that corresponds to a target, like multi-user target wants or graphical target wants. Disabling a service, prevent auto start. To prevent a service from starting automatically at boot time, sudo systemtool disable Apache service. This removes the symbolic link created by the enable command. Checking service status. This command is crucial for troubleshooting. It provides detailed information about a service's current state, whether it's active, running, enabled, disabled, and often shows the last few lines of its logged output. Systemtool status Apache service. You'll see output indicating if it's active and running, the process ID, memory usage, and recent log entries. Restarting a service. This command effectively performs a stop and then a start operation. Sudo systemtool restart Apache service. Use this when you've made changes to a service's configuration file that require a full reload. Reloading a service. Some services support a reload operation, which applies configuration changes without completely stopping and restarting the service. This is ideal for services like web servers, where you want to apply changes without dropping active connections. Sudo systemtool reload Apache service. Not all services support reload. If they don't, systemtool restart is your only option. Listing units. To list all currently loaded units, including services, targets, devices, etc. Systemtool list units. To list only services, systemtool list units type equals service. To list all available unit files, whether enabled or disabled, loaded or not. Systemtool list unit files. This shows the state column, indicating if a unit is enabled, disabled, static, or masked. Static means it's a dependency of another unit and cannot be enabled, disabled directly. Masked means it's completely disabled and cannot be started manually or enabled. Examining unit file contents. To see the content of a unit file as systemd interprets it, useful for checking overrides. Systemtool cat Apache service. 4.4 Understanding system targets. As mentioned, targets target units represent specific states or groups of services. They simplify the process of bringing a system to a desired operational level. Think of them as modern run levels. Common targets and their purposes. Multi-user target, the default non-graphical target. This state typically includes networking, login services, and essential background daemons, but no graphical display. It's often the default for server installations. Graphical target. This target depends on multi-user target and adds a display manager, like SDDM or GDM, to provide a graphical login screen. This is the typical default for desktop installations. Reboot target. Used for rebooting the system. Power off target, used for shutting down the system. Rescue target, a minimal system state often used for troubleshooting, typically providing only a root shell and basic services. Managing targets. Check the default target, system.get_default. This shows which target your system will try to reach upon boot, e.g., graphical target. Set the default target. To change the default boot target, e.g., for a server, you might want multi-user target. Sudo system.tool set default multi-user target. Switching targets temporarily. To change the system's state immediately without rebooting, sudo system.tool isolate multi-user target. This will stop all services not required by the new target and start any services needed by it. Be cautious, as isolate can disrupt running applications. 4.5 Journaled. Centralized logging with journaled. Traditional Linux systems often scatter log files across various directories in /var/log. While these still exist for some applications, Systemd introduces journaled, a centralized logging service that collects kernel messages, system service messages, and messages from applications, storing them in a structured, indexed binary format. Advantages of journaled. Centralized, all logs are collected in one place. Structured data, logs are stored with metadata like timestamp, service name, priority, process ID, making them easily filterable and searchable. Efficient, designed for speed and efficient storage. Secure, log data is protected from tampering and corruption. Using journaled, the journaled command is your window into the system journal. View all logs. Journaled. This displays all collected logs, starting from the oldest available entry. The output can be lengthy. Press Q to quit the viewer. Follow new logs, live view, to see new log entries as they happen, similar to tail F. Journaled F. Filter by service unit. View logs specifically for a particular service. Journaled U Apache service. Filter by time. Logs from the current boot. Journaled B. Logs from the previous boot. Journaled B. Logs since a specific time. Journaled since 2023 to 10 to 26/10/00. Logs within a specific range. Journaled since yesterday until now. Filter by priority. Systemd logs messages with different priority levels, e.g., error, warning, info, debug, to see only messages of a certain priority or higher. Journaled PR shows errors and critical failures. Priority levels range from 0, emerge, to 7, debug. Combined filters. You can combine filters. Journaled U SSHD service BP warning. Show warnings and errors for the SSH daemon from the current boot. Output formats. Output as plain text. Journaled U Apache service no pager output equals cat, useful for scripting. Other formats like JSON are also available. Persistent logging. By default, systemd logs are stored in a volatile file system in RAM, run log journal, and are lost on reboot. To make logs persistent across reboots, simply create the directory var/log/journal. Sudo mkdir p var/log/journal. Sudo system.tool restart, system journaled. After this, logs will be stored permanently on disk. 4.6 Creating custom system services. Conceptual. While many services come with their own unit files, as an administrator, you might occasionally need to create a custom service unit for a script or application that needs to run in the background. The process involves creating a new service unit file in etc. system. A basic service unit file would typically have 3 main sections. Unit contains a description of the unit and its dependencies. For example, description equals my custom Python script or after equals network target, meaning it starts after the network is up. Service defines the type of service, how it starts, and details about its execution. Key options include exec start equals, the command to run, working directory equals, where the command is executed, and user equals, which user the service runs as. Install specifies how the service should be installed, particularly which target it should be enabled under. For example, wanted by equals multi-user target. After creating or modifying a unit file, you must tell system to reload its configuration so it recognizes the changes. Sudo system.tool daemon reload. Only then can you enable and start your new custom service. This topic can become complex, but understanding the basic structure and the purpose of these sections provides a strong foundation. Conclusion: Systemed is far more than just a boot manager. It's a comprehensive system and service manager that centralizes control over nearly all aspects of your Arch Linux installation. By mastering the systemctl command, understanding the various types of systemed units, and leveraging the power of journoctl for logging, you gain fine-grained control and invaluable insight into your system's operations. This knowledge is not only essential for Arch Linux, but is highly transferable to almost any modern Linux distribution you'll encounter in your administrative career. With the ability to manage services, we now turn our attention to how your system organizes and stores data. In the next chapter, we will delve into file systems and storage management, exploring how to partition, format, and maintain your disk drives to ensure data integrity and accessibility. Chapter 5, File Systems and Storage Management, Organizing Your Data. Introduction. With your Arch Linux system now installed, and its core services under systemed command, we turn our attention to one of the most fundamental aspects of any operating system: how it manages and organizes data on its storage devices. File systems and storage management are the bedrock upon which all your applications, documents, and system configurations reside. A well-structured and properly maintained storage system is critical for performance, reliability, and data integrity. In the previous chapter, during installation, you conceptually touched upon partitioning disks. This chapter will expand on that, diving deeper into the concepts of block devices, various file system types, and the crucial role of mounting and the fstab file in making data accessible. We'll also explore more advanced topics like logical volume management, LVM, which offers incredible flexibility, and discuss essential tasks for monitoring and maintaining your disk space. Understanding these concepts will empower you to efficiently organize, secure, and troubleshoot your data on an Arch Linux system. 5.1 Disk Basics, from physical to logical storage. Before we delve into file systems, let's establish a clear understanding of the storage hardware itself. Block devices. At the lowest level, your computer interacts with storage devices, whether they are traditional hard disk drives, HDDs, solid-state drives, SSDs, or NVMe drives as block devices. A block device is a physical storage medium that stores data in fixed-size blocks, typically 512 bytes or 4 kilobytes. The operating system reads and writes these blocks of data. In Linux, block devices are represented as special files in the /dev directory. You'll typically encounter /dev/sdx, used for SATA-connected hard drives or SSDs. The X is a letter, B, C, etc., assigned sequentially as disks are detected. So /dev/sda would be your first detected disk, dev/sdb your second, and so on. Dev/NVMe XNY, used for NVMe non-volatile memory express, SSDs. Here, X often refers to the controller number and Y to the device number on that controller. For example, /dev/NVMe0, N1 would be the first NVMe drive on the first controller. Partitions. A single physical disk can be divided into several logical sections called partitions. Each partition can then be treated as a separate storage unit. This allows you to organize your disk space, isolating different types of data or operating systems. For example, you might have one partition for your operating system files and another for your personal documents. When you create partitions, you're essentially drawing boundaries on your physical disk. The information about these boundaries is stored in a partition table at the beginning of the disk. The two most common types of partition tables are Master Boot Record, MBR, an older standard that supports up to 4 primary partitions and a maximum disk size of 2 terabytes. It's still widely used, especially for older systems or specific boot requirements. GUID Partition Table, GPT, a newer, more modern standard that is part of the UEFI specification. GPT supports a virtually unlimited number of partitions and very large disk sizes, many zettabytes. It's the recommended standard for all new systems, especially those using UEFI firmware, as demonstrated in our installation. Why partition? Practical reasons. While you can technically install Arch Linux on a single root partition, creating multiple partitions offers several advantages for system administration. Data isolation. Separating your operating system from your user data, home, means if you need to reinstall the OS, your personal files remain untouched on their separate partition. Security and stability. Placing system logs /var/log or temporary files /tmp on dedicated partitions can prevent a runaway process that fills up disk space from crashing your entire system. Performance. Spreading input-output across different physical disks or different parts of the same disk can sometimes improve performance, though this is less significant for SSDs. Snapshots and backups. File system-level snapshots, like those offered by BTRFS or LVM, work best on dedicated logical volumes. Partitioning tools. Linux provides command-line tools for creating and managing partitions. fdisk, a text-based utility primarily used for MBR partitioning, though it can interact with GPT. gdisk, the GPT-specific counterpart to fdisk, highly recommended when working with GPT partition tables. Parted, a more powerful and modern command-line tool that supports both MBR and GPT and can perform operations on the fly. It's often used in scripts due to its non-interactive nature. All these tools display disk layout, allow you to create, delete, and modify partitions, and write changes to the disk's partition table. Remember the warning from installation. Parted or fdisk can erase data if used incorrectly, so always double-check your commands. 5.2 File systems, the data organizer. Once you've created partitions, they are just blank canvas. A file system is the structure that the operating system places on a partition or an entire disk to manage files and directories. It defines how data is stored, retrieved, and organized, converting raw blocks of data into a hierarchical structure that humans can understand. Think of a partition as a large, empty warehouse. The file system is the shelving system, inventory management software, and labeling system that allows you to store items, files efficiently, find them easily, and put them away without losing track. Common Linux file systems. Linux supports a wide array of file systems, each with its own strengths and weaknesses. ext4, fourth extended file system, the default workhorse. ext4 is by far the most common and widely used file system in Linux. It's the default for Arch Linux and many other distributions. Journaling. It's a journaling file system, meaning it keeps a log of changes before they are committed to the main file system. This significantly improves data integrity and recovery speed in case of an unexpected shutdown or power loss, as the file system can quickly replay the journal to restore consistency. Reliable and mature. ext4 is highly robust, stable, and well-tested, making it an excellent choice for general-purpose use, including your root and home partitions. XFS, performance for large files volumes. Originally developed by SGI for high-performance computing, XFS excels in scenarios involving very large files and volumes. It also handles many concurrent read-write operations efficiently. Journaling. Like ext4, XFS is a journaling file system. Common in servers, often preferred for /var, where logs and web server content might reside, and large data storage partitions on servers due to its strong performance characteristics. BTRFS, B-tree file system, modern and feature-rich. BTRFS is a copy-on-write (CoW) file system that offers advanced features aiming to address limitations of older file systems. Key features. Snapshots. Allows you to create snapshots of your file system at a particular point in time, which consume very little space initially. These are invaluable for quick backups and easy rollback in case of an update or configuration change gone wrong. Checksums maintains data integrity by storing checksums for both data and metadata, detecting and in some cases repairing silent data corruption, bit rot. Subvolumes. Similar to separate partitions within a single BTRFS file system, offering flexibility without fixed partition sizes. RAID-like functionality. Can manage multiple devices and provide software RAID capabilities. Growing popularity. While more complex than ext4, its features make it attractive for advanced users and certain server workloads where data integrity and easy rollback are paramount. FAT32 and NTFS. Interoperability. These file systems are primarily used for compatibility with Windows systems. FAT32 is an older, simpler file system often found on USB drives. NTFS is the default file system for Windows. Linux limitations. While Linux can read and write to both, they lack many Linux-specific features, like proper permissions management, and are not suitable for installing your Linux operating system on. An EFI system partition, ESP, on a UEFI system, however, must be formatted with FAT32. Creating file systems, MKFS commands. The command used to create a file system on a partition is typically MKFS followed by the file system type. To create an X4 file system on a partition, sudo mkfsxt4 dev/sda1. To create an XFS file system, sudo mkfsxfs dev/sda2. To create a btrfs file system, sudo mkfsbtrfs dev/sda3. To create a FAT32 file system for your EFI partition, sudo mkfsfat f32 dev/sda1. 5.3 Mounting an fstab. Making data accessible. Once you have formatted a partition with a file system, it's still inaccessible to your running Linux system. You need to mount it. What is mounting? Mounting is the process of attaching a file system to a specific directory in your existing directory tree. This directory is called a mount point. Once mounted, the contents of the file system on that partition become accessible through that mount point. For example, if you have a partition formatted with ext4 at dev/sdb1 and you want to access its contents under home, you would mount dev/sdb1 onto home. After mounting, ls-home would show you the files and directories on that partition. Temporary mounting, mount command. You can temporarily mount a file system using the mount command. Sudo mount/dev/sdb1/mnt/mydata. This command mounts dev/sdb1 to the directory mnt/mydata. The data will be accessible there until you unmount it or reboot your system. To unmount, you would use sudo umount/mnt/mydata. It can be useful for quickly accessing a USB drive or a temporary storage location. Persistent mounting, the /etc/fstab file. While temporary mounting is useful, you want your system to automatically mount essential partitions, like your root file system, home directory, or swap space, every time it boots. This is where the /etc/fstab file comes in. The /etc/fstab file system table is a crucial configuration file that lists all the file systems that should be mounted automatically at system startup, along with their mount points, file system types, and various mounting options. Each line in etc/fstab represents a file system entry and has 6 fields, separated by white space. File system, device. This specifies the device or partition to be mounted. It's highly recommended to use UUIDs, universally unique identifiers, rather than device names like /dev/sda1. UUIDs are unique identifiers assigned to each file system during formatting, ensuring that even if your disk device names change, e.g., if you add or remove storage, your system will always mount the correct partition. You can find a partition's UUID using the lsblkf command or blkid. Example: UUID equals B1 A to B3 C4 D5 E6 to 78 90 F1 G2 H3 I4 J5 K6 L7 M8. Mount point directory. This is the directory where the file system will be attached. For your root partition, this is. For your home partition, it might be home. Example: /home/boot/EFI. Type, file system type. The type of file system, e.g. ext4, XFS, BTRFS, VFAT for FAT32. Example: ext4 VFAT. Options, a comma-separated list of mounting options. These control how the file system is mounted and accessed. Common options include defaults. A common set of options: RW, Suede, Dev, Exec, Auto, Nouser, Async. RW, mount as read-write. Row, mount as read-only. No time, don't update access times on files. This can improve performance, especially for SSDs. Nafil, the system will continue booting even if the mount fails. Useful for external drives that might not always be connected. Discard, for SSDs, enables trim support, also known as discard, which helps maintain SSD performance and longevity. Exec allows execution of binaries on the file system. Noxec prevents execution of binaries, a security measure for partitions like /tmp. Remountro, for the root file system, allows remounting as read-only in certain circumstances for self-protection. For an EFI system partition, you often see umesc equals 0077, iacharset equals UTF-8, and the fmask and dmask options to ensure correct permissions. Dump backup strategy. Used by the dump command, an older backup utility, to determine which file systems to back up. A 0 means don't dump, 1 means dump. For most modern setups, 0 is common. Example, 0. Pass file system check order. Determines the order in which FSCK, file system check, checks file systems at boot. The root file system should be 1, other file systems that need checking should be 2, 0 means no check. Example, 0, 1, 2. Example, etc. /fstab entry. An entry for your root partition might look like this. UUID equals B1 A to B3 C4 D5 E6 to 78 90 F1 G2 H3 I4 J5 K6 L7 M8 /ext4 defaults, no time 0 1. Your EFI system partition would be UUID equals whatever your EFI UID /boot EFI VFAT umesc equals 007702. Always be careful when editing etc. /fstab. A mistake can prevent your system from booting. After making changes, you can test them by typing sudo mount a, which attempts to mount all entries in fstab that aren't already mounted. If no errors appear, your entries are likely correct. 5.4 Swap space, beyond physical memory. Swap space acts as a virtual extension of your system's RAM. When your physical memory, RAM, is full, the operating system can move less used pages of memory from RAM to swap space on your hard drive. This frees up RAM for active processes. While useful, swap space is significantly slower than RAM because it involves disk I/O excessive swapping, often called thrashing, can severely degrade system performance. You can implement swap in 2 ways. Swap partition, a dedicated partition on your disk formatted specifically as swap space. This is what we touched on during installation. To activate a swap partition, e.g. /dev/sda3, sudo swapun /dev/sda3. Add an entry to etc. /fstab to activate it at boot. UUID equals your swap UID, none swap defaults 00. Swap file, a regular file located on an existing file system, like your root partition, that is designated to act as swap. This offers more flexibility, as you can easily resize or remove it without repartitioning. To create a 4 GB swap file, recommended if you didn't create a swap partition or need more, create the file, sudo followcate L for G swapfil. Set restrictive permissions, sudo chmod 600 swapfil. Format for swap, sudo mkswap swapfil. Activate, sudo swapun swapfil. Add to fstab for persistence. Swapfil nenswap default 00. You can see your current swap usage with the swapon show command or free h. The recommended size for swap depends on your RAM and workload. For most desktops, a swap size between equal to RAM and twice RAM is often cited, but with modern RAM sizes, 16 GB plus, often 4 to 8 GB is sufficient. 5.5 Logical Volume Management, LVM, the flexible approach. For more complex storage needs, especially in server environments, Logical Volume Management, LVM, offers a powerful and flexible abstraction layer over physical storage devices. LVM allows you to pool physical disks or partitions into volume groups, and then slice them into logical volumes that behave like flexible, resizable partitions. LVM concepts, physical volumes, PVS. These are your underlying physical disks or partitions that have been prepared for use with LVM. Volume groups, VGS. One or more physical volumes are combined into a volume group. This creates a flexible pool of storage space from which you can allocate logical volumes. Logical volumes, LVS. These are essentially the flexible partitions that you create from the volume group. You format logical volumes with file systems, e.g. ext4, XFS, and mount them just like regular partitions. Benefits of LVM. Resizing. Logical volumes can be resized, grown, or shrunk on the fly, even while the file system on them is in use, without needing to repartition the entire disk. This is a massive advantage compared to static partitions. Snapshots. LVM supports creating snapshots of logical volumes. These are point-in-time copies that can be used for backups or to test changes, allowing you to revert to the snapshot if something goes wrong. Disk pooling. You can add new physical disks to an existing volume group to expand your storage pool without downtime. Portability. Entire volume groups can be moved between systems relatively easily. Conceptual LVM workflow. Initialize physical volumes. pvcreate/dev/sdan/dev/sdbn, prepare partitions for LVM. Create volume group. vgcreate mivc dev/sdan/dev/sdbn, combine PVs into a VG. Create logical volume. lvcreate L100G n mylogicalvolume mivc. Create a 100 GB LV within mivc. Format logical volume. mkfsxt4 dev/mapper/mivc mylogicalvolume. Format the LV. Mount and add to fstab. Mount the LV to a mount point and add its entry to /etc/fstab using its UUID or the /dev/mapper/path. While LVM introduces a layer of abstraction, its flexibility and advanced features make it an indispensable tool for managing storage in dynamic environments. 5.6 Monitoring disk space and usage. Effective system administration involves constantly monitoring your resources, and disk space is no exception. Running out of disk space can lead to system instability, application crashes, and data loss. df disk free. This command reports file system disk space usage. dfh shows human readable output, megabytes, gigabytes. dfi reports inode usage. Inodes represent files or directories. Running out of inodes can prevent file creation even if there's free space. Do disk usage. This command estimates file space usage. It summarizes disk usage for specified files or directories. Do sh path to directory. Summarizes the total size of a directory in human-readable format. Do h max depth equals 1 path to directory. Shows the size of subdirectories 1 level deep. These commands are invaluable for identifying what's consuming disk space. lsblk list block devices. This command provides a tree-like list of all block devices, disks, partitions, LVM volumes, and their mount points. It's excellent for visualizing your entire storage layout. lsblkf shows file system type and UUIDs, which is very useful for fstab configuration. 5.7 Maintenance and troubleshooting tips. File system checks, FSCK. Despite journaling, file systems can sometimes become inconsistent due to abrupt power loss or hardware issues. The FSCK, file system check, utility is designed to scan and repair file system errors. It's typically run automatically at boot if the system detects an unclean shutdown, based on the pass field in etc/fstab. You should never run FSCK on a mounted file system, as it can cause data corruption. To check your root file system, you'd typically boot from a live USB, like your Arch installation media, and run the check from there. Example, sudo fsck fdev/sda1, the F flag forces a check. Dealing with full disks, identify the culprits using do and df. Clear package caches, e.g. sudo pacman scc. Clean old log files, check var/log/journal/ or var/log/ for large files. Remove unused software. Clear temporary files in /tmp. Delete old snapshots if using BTRFS or LVM. Corrupt file systems /data recovery. While FSCK can fix many issues, severe corruption might require specialized data recovery tools, e.g. test disk, photorec. The most important strategy against data loss, however, is regular backups. No amount of file system wizardry can compare to having a recent, off-site copy of your critical data. Conclusion. Storage management is a cornerstone of system administration. By understanding the hierarchy from physical block devices to partitions, file systems, and logical volumes, you gain the ability to structure your data intelligently and efficiently. Mastering the mount command, configuring fstab, and leveraging advanced features like LVM are essential skills for any Linux administrator. Combined with regular monitoring and diligent maintenance, you can ensure your Arch Linux system's data is organized, secure, and always available. With our discussion on organizing data complete, the next logical step is to connect your Arch Linux system to the broader world. In Chapter 6, we'll dive into network configuration, exploring how to get your system communicating effectively with other devices and the Internet. Chapter 6, Network Configuration, Connecting Your Arch System. Introduction. After successfully installing your Arch Linux system and mastering the art of package management and system services, the next crucial step is to connect your system to the wider world. In today's interconnected environment, a computer is largely isolated and limited without network access. Whether your Arch system is a personal workstation, a server, or a development machine, robust and reliable network configuration is paramount. From accessing websites and downloading updates to hosting services and communicating with other devices, networking is the fundamental backbone of modern computing. Unlike some distributions that come with a pre-selected and pre-configured network manager, Arch Linux, true to its do-it-yourself philosophy, offers you the choice. This flexibility allows for highly optimized and specific network setups, but it also means you, the administrator, are responsible for its configuration. This chapter will guide you through the essentials of network configuration on Arch Linux. We'll explore the underlying concepts, introduce the primary tools available, and walk through configuring both wired and wireless connections, along with troubleshooting common network issues. 6.1. Identifying your network interfaces. Before you can configure a network connection, your system needs to recognize its network hardware. Network interface cards, or NICs, are the physical components that allow your computer to connect to a network. Linux assigns specific names to these interfaces. Ethernet interfaces. These are typically named EMP-XSY, e.g., EMP03, based on their physical location on the PCI bus, or sometimes ETH0, ETH1, etc., especially on older systems or during the installation environment. Wireless interfaces. These are usually named WLP-XSY, e.g., WLP2S0 or WLAN0, WLAN1. Loopback interface. Every Linux system has a special virtual interface called the loopback interface, usually named LO. It always has the IP address 127.0.0.1 or 1 for IP6. This interface is used for communication between processes on the same machine and is vital for many system services. You can often test parts of your network stack even without a physical connection by pinging the loopback address. To view the network interfaces present on your system, along with their current status and assigned IP addresses, you'll use the IP command, a powerful utility that has largely replaced the older ifconfig for network management. Type in your terminal, IP. The output will list all detected network interfaces. For each interface, you'll see its name, like LO, EMP03, its MAC address, a unique hardware identifier, and any assigned IP addresses. You'll also see its state, such as UP or DOWN, indicating whether the interface is active. 6.2 Essential Network Concepts. To effectively configure a network, it's helpful to understand a few fundamental networking concepts. IP address. An IP address, Internet Protocol address, is a unique numerical label assigned to each device connected to a computer network that uses the Internet Protocol for communication. Think of it as your device's street address on the network. IP addresses can be IP4, e.g., 192.168.1.100, or the newer IP6, e.g., 2001, 0db8, 1. Private Vs Public IP. Private IP addresses are used within your local network, e.g., home or office LAN, and are not directly routable on the public internet. Public IP addresses are assigned to your network by your internet service provider, allowing your devices to communicate globally. A router performs network address translation, NAT, to allow multiple devices with private IPs to share a single public IP. Subnet mask. The subnet mask, e.g., 255.255.255.0 or 24 in CIDR notation, defines which part of an IP address represents the network portion and which part represents the host portion. It determines the size of your local network and which devices are considered local. Default gateway. The default gateway is the IP address of the router or device that connects your local network to other networks, like the internet. Your computer sends all traffic destined for outside the local network to this gateway. Without a correctly configured default gateway, your system can only communicate with other devices on its immediate local network. DNS, Domain Name System. DNS is often called the phone book of the internet. When you type a website address like google.com into your browser, your computer doesn't know its numerical IP address. DNS servers translate human-readable domain names into machine-readable IP addresses. Without DNS, you'd have to remember the IP address for every website you want to visit. DHCP, Dynamic Host Configuration Protocol. For most home and client systems, your IP address and other network settings are assigned automatically by a DHCP server, often running on your router. This simplifies network setup significantly. Static IP address. In contrast to DHCP, a static IP address is manually configured on a device and remains constant. This is common for servers, network printers, or other devices that need a consistent, predictable address. 6.3 Network Configuration Tools in Arch Linux. Given Arch's principle of choice, there isn't one single, predetermined way to manage your network. Instead, you select the tool that best fits your needs. The two most prominent and widely used methods are Network Manager and System Networked. Network Manager. What it is? Network Manager is a daemon that aims to make networking configuration and setup as painless and automatic as possible. It's especially popular on desktop and laptop systems due to its robust support for wired, wireless, mobile broadband, and VPN connections. It provides both graphical user interfaces, integrated into desktop environments like GNOME, KDE, XFCE, and a powerful command line interface called nmcli. Why use it? User-friendly, automates connection switching, handles various connection types, reliable. Recommended for most desktop and laptop users. System Networked. What it is? This is System's native daemon for managing network configurations. It uses simple, declarative INI-style configuration files located in etc. systemed network. It's lightweight and well-integrated into the systemed ecosystem. Why use it? Good for server environments where you want minimal dependencies, predictable behavior, and don't need the complexity of Network Manager. Requires more manual configuration. Other legacy, Nectal. Arch Linux also has Nectal, a simple command line utility for managing network profiles. While it was once a primary tool, its usage for general wired and wireless configuration has largely been superseded by System Networked and Network Manager, as they offer more comprehensive solutions and better integration with other services. You might still encounter it in some custom setups, but for most daily administration, it's less common now. For the purpose of this chapter, we'll focus on Network Manager as it is the most common and versatile choice for general use, and briefly touch on System Networked for its server-oriented advantages. Remember, you should generally use only one of these network management daemons to avoid conflicts. 6.4 Configuring wired connections. Wired Ethernet connections are typically the simplest to configure. Using Network Manager, recommended. If you chose to install Network Manager during the initial setup, as recommended, configuring a wired connection is usually automatic. Enable and start the service. Ensure Network Manager is running and set to start on boot. Type sudo systemctl enable now Network Manager. The now flag means it starts immediately after enabling. Connect the cable, plug in your Ethernet cable. Network Manager should automatically attempt to obtain an IP address via DHCP. Verify connection to see your interface's IP address, IP. To check that you have a default gateway, a route to the internet. IPR, look for a line starting with default. To test internet connectivity, ping google.com. You can also use Network Manager's command line interface to check status. nmcli connection show or nmcli device show emp03, replace emp03 with your actual Ethernet interface name. For a static IP address with Network Manager, using nmcli. If a DHCP server is not available or you require a fixed IP address for a server, you can configure it manually. Add a new connection profile. Type sudo nmcli connection, add type Ethernet con name, my static head. If name emp03 ip4 no, replace emp03 with your interface name. This command creates a new Ethernet connection profile named mystatichead associated with emp03 and sets ip4 to manual. Set IP address, gateway, and DNS servers. Type sudo nmcli connection modify mystatichead ip4. Addresses 192.168.1.100/24 ip4. Gateway 192.168.1.1 ip4. DNS 8.8.8.88.8.4.4. Autoconnect yes. This sets your desired IP address, 192.168.1.100, with its subnet mask, 24. The gateway, 192.168.1.1, and 2 public DNS servers, Google's 8.8.8.8 and 8.8.4.4. Autoconnect yes ensures it connects automatically on boot. Bring up the connection. Type sudo nmcli connection up mystatichead. Network Manager will now attempt to activate this configuration. Using System Networked for servers or minimal setups. If you prefer System Networked, you'll first need to disable Network Manager if it's currently running. Disable Network Manager. Type sudo systemctl stop Network Manager. Type sudo systemctl disable Network Manager. Enable System Networked. Type sudo systemctl enable now System Networked. Create configuration files. You'll create ini-style files in etc. System Network. The file names often start with numbers for ordering, e.g., 20-wired.network. For DHCP, create etc. System Network 20-wired.network and add the following content. Match. Name equals emp03. Replace with your Ethernet interface name. Network. DHCP equals yes. For static IP, create etc. System Network 30-static-eth.network and add. MAT. Name equals emp03. Replace with your Ethernet interface name. Network. Address equals 192.168.1.100/24. Gateway equals 192.168.1.1. DNS equals 8.8.8.88.8.4.4. Remember to save and close the file. Restart System Networked. Type sudo systemctl restart System Networked. You can then IP and ping to verify your connection. 6.5 Configuring wireless connections, Wi-Fi. Wireless configuration is inherently more complex than wired due to the need for scanning, authentication, like WPA2, and then obtaining an IP address. Using Network Manager, recommended for Wi-Fi. Network Manager excels at Wi-Fi management, making it the easiest and most robust option for wireless. Ensure WPAS applicant is installed. Network Manager relies on the WPAS applicant package to handle the technical details of Wi-Fi encryption and authentication. You likely installed it during the initial packstrap, but if not, type sudo pacman s WPAS applicant, enable and start Network Manager, as shown in the wired section. Scan for Wi-Fi networks, type nmcli device Wi-Fi rescan. List available networks, type nmcli device Wi-Fi list. This will show SSIDs, network names, signal strength, and security protocols. Connect to a Wi-Fi network. Type sudo nmcli device Wi-Fi connect, your WAFI SSID, password your Wi-Fi password. Replace quotes with your actual SSID and password. Network Manager will attempt to connect and obtain an IP address via DHCP. Verify connection. Use IP and ping google.com. Manual configuration with WPAS applicant and DHCP-CD. Advanced. For minimal server setups or custom scenarios where Network Manager isn't desired, you can manually configure Wi-Fi. This involves configuring WPASApplicant for authentication and then a DHCP client, like DHCP-CD, to get an IP address. Install WPASApplicant and DHCP-CD. Type sudo pacman s wpasapplicant DHCP-CD. Generate WPASApplicant config. Type sudo wpasphrase, your WIFI-SSID, your Wi-Fi password, /etc/ wpasapplicant wpasapplicant wlp2s0.conf. Replace wlp2s0 with your wireless interface. This creates a basic configuration file with your network's SSID and a hashed password. Enable and start WPASApplicant and DHCP-CD services. Type sudo systemctl enable now WPA supplicant at WLP2S 0.service. Type sudo systemctl enable now DHCP-CD at WLP2S 0.service. That WLP2S 0 tells system to use this specific interface for the service. This method gives you very fine-grained control, but as you can see, it's more verbose and requires careful placement of configuration files. For most users, Network Manager is significantly simpler. 6.6 DNS and name resolution with systemd resolved. In Arch Linux, systemd resolved is the default service responsible for name resolution, translating domain names to IP addresses. It typically manages the etc/resolve.conf file, which is often a symbolic link pointing to a file managed by systemd resolved. Checking DNS status? Type resolvectl status. This command will show you the configured DNS servers for each interface and their current status. Configuring DNS servers with Network Manager. DNS servers are usually obtained automatically via DHCP. If you need to set them manually, you do so within the connection profile, as demonstrated in the static IP section for wired connections. With system networked, you specify DNS servers directly in the network configuration files, e.g., DNS equals 8.8.8.88.8.4.4. Manual override temporary. For temporary testing, you can directly edit etc/resolve.conf, but changes are typically overwritten by your network management service. If you hardcode DNS in Network Manager or System Networked, they will be used. 6.7 Troubleshooting network issues. Network problems can be frustrating, but with the right tools and a systematic approach, you can diagnose and resolve most issues. Check interface status. Is the interface up? IP. Is there an IP address assigned? Is it the correct one? IP. Is the network cable plugged in for wired? Is the Wi-Fi adapter enabled? Check routing table. Do you have a default gateway? IPR. If not, your system can't reach anything outside its local network. Test connectivity. Ping, local network. First, ping your default gateway's IP address. Ping 192.168.1.1, replace with your gateway. If this fails, the problem is likely on your machine or within your local network, e.g., incorrect IP address, cable issue, router problem. Internet connectivity, IP only. If the gateway responds, ping a well-known public IP address directly, bypassing DNS, such as Google's DNS server. Ping 8.8.8.8. If this works but ping google.com fails, your network connection is fine, but you have a DNS problem. Internet connectivity with DNS, ping google.com. If this works, your network is fully functional. Diagnose DNS issues, enslookup or dig. To verify DNS resolution, try enslookup google.com or dig google.com. If these commands fail to resolve the name to an IP address, then your DNS servers are either misconfigured, unreachable, or non-functional. Check your etc/resolve.conf contents or your network manager's DNS settings. Check open ports and services, SS. If you're trying to reach a service on another machine, e.g., a web server, and it's not responding, check if the service is listening on the correct port on the destination machine. SSTOLN shows listening TCP and UDP ports. Trace the route, traceroute, or tracepath to see the path packets take to reach a destination and identify where connectivity might be breaking. Traceroute google.com or tracepath google.com. Each hop represents a router in the path. Check service logs, journalctl, Look for error messages related to your network manager, Journoctal U Network Manager or Journoctal U System Networked. This can provide specific reasons for connection failures. Firewall. Remember that a firewall, which we'll discuss in a later chapter on security, might be blocking incoming or outgoing connections. If you can ping but can't access a specific service, a firewall is a common culprit. Temporarily disabling the firewall with extreme caution in a controlled environment can help rule it out as the cause. Anecdote. I once spent hours trying to figure out why a newly deployed Arch server couldn't connect to our internal network resources, even though it could ping external websites. IP showed a valid address, IPR had a default gateway, and ping 8.8.8.8 worked. The breakthrough came when I used ping internal.companylocal, and it failed, while ping 10.0.0.50, the actual IP, succeeded. It was a simple DNS misconfiguration. The server hadn't been given the internal DNS servers, so it couldn't resolve internal hostnames. This highlighted the importance of systematically using ping with both IP addresses and hostnames to distinguish network and DNS issues. Conclusion. Connecting your Arch Linux system to a network is a fundamental administrative task, enabling it to communicate with other devices and access the vast resources of the Internet. By understanding the core network concepts like IP addresses, subnets, and DNS, and by mastering command line tools like IP and ping, you're equipped to configure and troubleshoot connections effectively. The choice between Network Manager for its user-friendliness and System Networked for its leaner, server-focused approach allows you to tailor your network setup to your specific needs, truly embracing the Arch philosophy of control. With your system now fully online and communicating efficiently, our next step is to control who can access it and what they can do. In the following chapter, we'll delve into user and group management, ensuring your system is both accessible to authorized individuals and secure from unauthorized access. Chapter 7, User and Group Management, Permissions and Access Control. Introduction. So far, you've built your Arch Linux base system, learned to manage its software with Pacman and the AUR, gained control over its services using Systemed, and established its connection to the network. These are the mechanical aspects of bringing your system to life. Now, we shift our focus to the human element, managing who can access your system, what they can do once inside, and how their actions interact with the files and resources on your machine. This is the realm of user and group management, complemented by the critical concept of file permissions. Effective access control is not just about security, it's also about maintaining order and preventing accidental damage. Whether your Arch Linux machine is a multi-user server, a development workstation shared with team members, or even a personal desktop, correctly configuring user accounts, groups, and file permissions is paramount. It ensures that system integrity is preserved, sensitive data is protected, and users only have the necessary privileges to perform their duties. This chapter will guide you through the fundamental Linux concepts of users, groups, and the intricate system of file permissions, providing you with the tools to master access control on your Arch Linux system. 7.1 User Accounts, the foundation of access. Every interaction with a Linux system, whether local or remote, is performed under a specific user account. A user account is a unique identity that allows a person, or a system service, to log in and interact with the operating system. Understanding user attributes. Each user account has several key attributes. Username, a unique name chosen by the administrator, e.g., John Webuser. User ID, UID, a unique numerical identifier. Linux internally uses UIDs rather than usernames. User IDs from 0 to 999 are typically reserved for system accounts, e.g., root is always UID 0, daemon might be 1. Regular user accounts usually start from 1000. Password, a secret string known only to the user, used for authentication. Home directory, the default directory where the user's personal files are stored, e.g., Home John. Login shell, the program that provides the command line interface when the user logs in, e.g., bin bash /bin/zsh. The root user, the superuser. During installation, you set a password for the root user. The root user UID0 is the superuser or administrator. This account has absolute power over the entire system, capable of performing any operation, accessing any file, and modifying any configuration. While root is essential for system administration, it should never be used for daily tasks or casual logins. Logging in as root carries significant risks. Accidental damage. A single misplaced command executed as root can irrevocably damage your system. Security vulnerability. If the root account is compromised, the attacker gains complete control of your system. Lack of accountability. When multiple administrators share the root password, it's impossible to track who made which changes. The principle of least privilege dictates that users, including administrators, should only have the minimum permissions necessary to perform their tasks. This is why we created a regular user account during installation and configured sudo access, rather than encouraging direct root login. Listing users. To view the user accounts on your system, you can inspect the /etc/passwd file. However, a more structured way is to use the getInt command. Type getInt passwd. This command retrieves entries from system databases, including the password file. Each line typically contains username password placeholder, UID GID, comment home directory shell. Adding users userad. To create a new user account, you use the userad command. Type sudo userad msbin bash g users g wheel audio video nuser. Let's break down the common options. This is crucial and tells userad to create the user's home directory /home/nuser. Without it, the user would have no personal directory. Sbin bash sets the user's default login shell to bash. Other common shells are /bin/zsh, /bin/sh. G-users assigns users as the user's primary group. Every user must belong to at least one primary group. G-wheel audio video adds the user to supplementary groups, e.g., wheel for sudo access, audio and video to allow access to sound and display hardware. You can specify multiple supplementary groups separated by commas. Nuser. This is the desired username. Setting passwords passwd. After creating a user, their account is locked until a password is set. Type sudo passwd nuser. You will be prompted to enter a new password twice. Choose a strong, complex password not easily guessed. Modifying users, usermod. The usermod command allows you to change a user's attributes after creation. Type sudo usermod lnusername oldusername to change login name. Type sudo usermod dnew home path nuser to change home directory. Type sudo usermod /bin/zsh nuser to change login shell. Type sudo usermod ag sudo developers nuser to add user to supplementary groups. A appends them, G specifies the groups. Without A, G would replace all existing supplementary groups. Type sudo usermod lnuser to lock a user's password, preventing them from logging in. Type sudo usermod unuser to unlock a user's password. Deleting users, userdl. To remove a user account, type sudo userdl nuser. This command removes the user's entry from /etc/passwd. However, it leaves their home directory and mail spool intact. Type sudo userdl rnuser. The R option is generally preferred, as it also removes the user's home directory and mail spool, effectively cleaning up all associated files. Switching users, su and sud. Su substitute user. This command allows you to switch to another user account. Type su nuser, the hyphen, ensures you get the new user's environment, including their home directory and path. You will be prompted for nuser's password. If you don't specify a username, it defaults to root. Sudo superuserdo. This is the preferred method for regular users to execute commands with elevated privileges. It allows you to run a single command as another user, by default root, without directly knowing the root password. Type sudo pacman shtop. You will be prompted for your own password. Sudo checks the etc/sudoers file to see if your user account is permitted to execute the command. This file is typically configured to allow members of the wheel group to use sudo. As we mentioned during your installation, you enable this by uncommenting the line %wheel all equals all using the vsudo command. Important note, Always use vsudo to edit etc/sudoers. It checks for syntax errors before saving, preventing you from locking yourself out of sudo access. 7.2 Groups, organizing permissions. While user accounts define individual identities, groups are used to logically organize users and assign permissions collectively. Instead of assigning permissions to each individual user, you assign permissions to a group and then add users to that group. This simplifies management, especially in environments with many users. Primary versus supplementary groups. Primary group. Every user must belong to one primary group. When a user creates a new file or directory, its group ownership is automatically set to the user's primary group. Supplementary or secondary groups. Users can be members of multiple supplementary groups. These grant additional permissions, e.g., access to specific hardware, a shared directory, or administrative privileges like sudo access. Understanding group attributes. Each group has group name, a unique name, e.g., users, wheel, developers. Group ID, GID, a unique numerical identifier. Listing groups. Group information is stored in the etc. group file. Type, getInt group. This command lists all groups and their members. Each line typically contains group name, password placeholder, GID, member list. Adding groups, grouped. To create a new group, type sudo grouped developers. Modifying groups, groupmod. To change a group's name, type sudo groupmod n new group name old group name. Deleting groups, groupdel. To remove a group, type sudo groupdel old group name. Viewing a user's groups. To see which groups a specific user belongs to, type groups username. Type id username provides more detailed information including UID, GID, and all group memberships. 7.3 File permissions. The gatekeepers of access. The Linux file system has a robust permission system that controls who can read, write, or execute files and directories. This is critical for security and system stability. The 3 permissions. For every file and directory, there are 3 fundamental permissions. Read R. Files allows viewing the contents of the file. Directories allows listing the contents of the directory, i.e., seeing what files and subdirectories are inside. Write W. Files allows modifying or deleting the file. Directories allows creating, deleting, or renaming files and subdirectories within that directory, even if you don't own the file. Execute X. Files allows running the file as a program or script. Directories allows entering the directory, accessing its subdirectories, or files within it, even if you cannot list its contents. If a directory is missing the execute bit for you, you can't CD into it or reference files by their full path. The 3 user categories. Permissions are applied separately for 3 categories of users. Owner, U, the user who owns the file or directory. Group, G, the group that owns the file or directory. Others, O, all other users on the system who are not the owner and are not members of the owning group. Viewing permissions, LSL. The LSL command is your primary tool for viewing file and directory permissions. Type LSL in your home directory. The output looks something like this. RWXRWR, 1 username group name 4096, oct 2610 filename txt. DRWXRXRX 2, username group name 4096, oct 2610 directory name. Let's break down the first 10 characters. First character indicates the file type, regular file. D, directory. L, symbolic link. B, block device. C, character device. Characters 2 to 4. Permissions for the owner, RWX. Characters 5 to 7. Permissions for the group, RW. Characters 8 to 10. Permissions for others, R. So RWXRWR means it's a regular file. The owner has read, write, and execute permissions, RWX. The group has read and write permissions, RW. Others have only read permission, R. Changing permissions, chmod. The chmod command is used to change file and directory permissions. It can be used with either octal numerical or symbolic notation. Octal numerical notation. This is very common and efficient. Each permission maps to a number, R equals 4, W equals 2, X equals 1. Sum the numbers for each category. RWX equals 4 plus 2 plus 1 equals 7. RW equals 4 plus 2 plus 0 equals 6. R, x equals 4 plus 0 plus 1 equals 5. R equals 4 plus 0 equals 4. To change permissions, using octal notation, sudo chmod owner permissions others permissions, file name, common file permissions, 644 RWRR, owner can read write, group others can only read. Good for regular text files. 755 RWXRXRX, owner has full permission, group others can read execute. Good for executable scripts or common directories that others should be able to enter and list. Common directory permissions. 755 DRWXRXRX, owner has full permission, group others can enter and list. This is a common default for home directories, often 700 or 750 for privacy, and general directories. Example, sudo chmod 644 myfiletxt. Symbolic notation. This syntax is more verbose, but often clearer for specific adjustments. It uses u owner, g group, o others, a all plus add permission, a remove permission, equals set exact permission. Chmod u plus x miscript sh, add execute permission for the owner. Chmod gw sumfiletxt, remove write permission for the group. Chmod o equals rwx sumdir, set exact permissions for others to read, write, execute. Chmod arw sharedir, remove read and write permissions for everyone. Changing ownership chown, chgrp. Chown change owner, changes the user owner of a file or directory. Type, sudo chown owner filename txt. Chgrp change group, changes the group owner of a file or directory. Type, sudo chgrp new group filename txt. You can change both user and group owner simultaneously with chown. Type, sudo chown owner new group filename txt. To apply changes recursively to contents of a directory, use cautiously. Type, sudo chown rnewner new group mydirectory / 7.4 special permissions. Beyond the basics, Linux also has 3 special permission bits that offer powerful but potentially risky capabilities. setuid, set user ID, effect on files. When an executable file has the setuid bit set, it runs with the permissions of the file's owner, not the user executing it. Common use case. The passwd command is a classic example. It needs to write to a restricted file, etc. shadow, to change passwords, which a normal user is not allowed to do. With setuid, passwd temporarily gains root privileges to perform its function. Security risk. Because setuid programs run with elevated privileges, they are a common target for attackers and must be written very securely. Notation. Appears as an S in the owner's execute position, RWSRXRX. Chmod. Chmod u plus S filename or chmod 4755 filename. Setgid, set group ID, effect on files. When an executable file has the setgid bit set, it runs with the permissions of the file's group owner. Effect on directories. When a directory has the setgid bit set, any new files or subdirectories created within it will automatically inherit the group ownership of that directory, rather than the primary group of the user who created them. This is incredibly useful for shared project directories. Notation. Appears as an S in the group's execute position, RWXRWSRX for files, DRWXRWSRX for directories. Chmod. Chmod g plus S filename directory or chmod 2775 directory. Sticky bit. Effect on directories. When the sticky bit is set on a directory, files created within that directory can only be deleted, renamed, or moved by their owner, the directory's owner, or the root user. Even if a user has write permission to the directory, they cannot delete or rename files they don't own. Common use case. The /tmp directory almost always has the sticky bit set drwxrwxrwt. This prevents users from deleting each other's temporary files, even though /tmp is globally writable. Notation. Appears as a T in the other's execute position, drwxrwxrwt. If others don't have execute permission, it's an uppercase T, drwxrwxrwt. Chmod. Chmod plus T directory or chmod 1777 directory. Default permissions umesc. The umask command determines the default permissions for new files and directories created by a user. It's a mask that removes permissions. For instance, a umask of 22 would result in default permissions of 755 for directories. 777, 22 equals 755, and 644 for files. 666, 22 equals 644. Understanding umask can help you troubleshoot why new files aren't getting the permissions you expect. 7.5 Access Control Lists, ACLS, beyond basic permissions. While traditional Linux permissions, user, group, others are powerful, they have a limitation. They only allow control for one specific user and one specific group. What if you need to grant specific permissions to multiple distinct users, or to a user who isn't in the file's primary group, without changing the file's primary group? This is where access control lists, ACLS, come in. ACLs provide a more granular and flexible way to manage permissions. They allow you to define permissions for arbitrary users and groups beyond the traditional owner, group, and others. Viewing ACLS, get facle filename. Setting ACLS. Set facle mu username, permissions filename, or set facle mg, group name, permissions filename. ACLS are an advanced topic, and for most common scenarios, traditional permissions suffice. However, for complex multi-user environments or specific application requirements, ACLs offer the necessary flexibility. You'll need to ensure the ACL package is installed, sudo pacman s-acl, and that your file system, e.g., ext4, is mounted with ACL support enabled. Often ACL is included in defaults mount options. 7.6 Best Practices for User and Group Management. Effective user and group management is a continuous process. Here are some best practices. Adhere to the principle of least privilege. Grant users and groups only the permissions they absolutely need. Avoid giving users sudo access or adding them to the wheel group unless their role truly requires it. Use strong passwords. Enforce password complexity policies and encourage users to use unique, strong passwords. Consider using password managers. For remote access, prioritize SSH key-based authentication over passwords. Regular audits. Periodically review user accounts. Are all accounts still needed? Are users in the correct groups? Are file permissions appropriately set? Tools mentioned in the previous chapter, like Journoctl for auditing sudo usage, can be helpful here. Automate if possible. For larger environments, consider configuration management tools, like Ansible or Puppet, to automate user group creation and permission setting, ensuring consistency. Document everything. Keep clear records of user roles, group assignments, and any custom permission configurations. Case study snippet. In a small development team, they initially granted everyone sudo access to their shared Arch Linux server. As the team grew, a new developer accidentally deleted a critical configuration file during a minor update. Recovering from backup took hours of downtime. After this incident, they implemented stricter user management. Limited sudo, only lead developers and sysadmins retained full sudo privileges. Dedicated groups. New groups were created, e.g., webdevs, debadmins, specific permissions. Directories for web code were owned by webuser, webdevs, and had write permissions only for the webdevs group, with setgid enabled. This ensured new files inherited the webdevs group, allowing collaboration without granting full system access. This incident underscored that while sudo provides ease, granular control over users, groups, and permissions is the ultimate safeguard against both malicious and accidental system compromise. Conclusion: user and group management, alongside a solid understanding of file permissions and access control, forms a critical pillar of system administration on Arch Linux. By carefully assigning roles, leveraging the power of groups, and meticulously configuring file permissions, you can create a secure, organized, and reliable environment for all users. This knowledge is not merely about preventing unauthorized access, but about engineering a system where every action is intentional and its impact predictable. With your system now securely set up for multiple users, the next logical step is to delve deeper into overall system security. In the following chapter, Essential Security Practices, Fortifying Your Arch System, We will build upon these foundational access controls to discuss network security, firewalls, and other crucial measures to protect your Arch Linux installation from external threats. Chapter 8, Essential Security Practices, Fortifying Your Arch System. Introduction. In the previous chapters, we focused on building, managing, and connecting your Arch Linux system. Now it's time to address a topic of paramount importance: security. In an increasingly interconnected world, securing your system isn't a luxury, it's an absolute necessity. Whether your Arch machine hosts critical data, provides essential services, or simply connects to the internet, it's a potential target. Security, however, is not a one-time setup. It's a continuous process, a mindset, and an ongoing commitment. The Arch way of system administration, with its emphasis on minimalism and user control, offers a powerful foundation for a secure system, but it also places a significant responsibility on you, the administrator. There are no wizards to magically secure your system. You must actively configure and maintain its defenses. This chapter will guide you through essential security practices for your Arch Linux installation. We'll cover everything from fundamental system hardening and firewall configuration to protecting against brute force attacks and implementing a robust backup strategy. By the end, you'll have a comprehensive understanding of how to fortify your Arch Linux system against common threats and maintain its integrity. 8.1. The Arch Way of Security. Empowerment and Responsibility. Arch Linux's design philosophy inherently contributes to its security posture, but it also necessitates your active involvement. Minimalism as a security feature. The Keep It Simple, KISS principle means that a default Arch installation is incredibly minimal. This results in a smaller attack surface, fewer installed packages, fewer running services, and less code generally means fewer potential vulnerabilities for attackers to exploit. You only install what you need, reducing bloat and thus reducing risk. Bleeding edge software. The rolling release model ensures you always have the latest software versions. This is a double-edged sword. While new features can introduce new bugs, security patches are generally available and deployable very quickly after they are released by upstream developers. This means vulnerabilities are patched more rapidly than on distributions with slower release cycles. Your responsibility. Arch doesn't make security decisions for you. It provides the tools and the flexibility. You are empowered to build a system precisely to your needs, but this empowerment comes with the responsibility of securing it yourself. This means diligently applying updates, configuring services securely, and understanding the implications of your choices. There's no secure by default wizard. It's secure by careful configuration. This active engagement fosters a deeper understanding of security mechanisms, which is invaluable for any system administrator. 8.2. Basic System Hardening. System hardening refers to the process of making your operating system and applications more secure by reducing their vulnerability. Secure passwords. This is the most basic, yet often overlooked security measure. Complexity. Enforce strong passwords for all user accounts, especially for the root user and any accounts with pseudo privileges. A strong password should be long, at least 12 to 16 characters. A mix of uppercase and lowercase letters, numbers, and symbols, and not be easily guessable. Avoid personal information, dictionary words, or common sequences. Uniqueness. Never reuse passwords across different systems or services. Password management. Encourage the use of a password manager to help users create and store complex, unique passwords. SSH security for remote access. Secure Shell, or SSH, is the primary way to remotely administer Linux systems. Securing your SSH configuration is paramount. The SSH server's configuration file is typically located at /etc/ssh/sshDconfig. After making any changes to this file, remember to restart the SSH daemon. Sudo systemctl restart SSHD service. Disable root login. Never allow direct SSH login to the root account. This prevents brute force attacks directly targeting the most powerful account. In etc/ssh/sshDconfig, ensure permaroot login is set to no. You would then log in with a regular user account and use sudo for administrative tasks, as discussed in Chapter 7. Use key-based authentication. This is significantly more secure than passwords. You generate a pair of cryptographic keys, a private key kept secret on your local machine, and a public key placed on the remote server. When you try to connect, the server challenges your client, and they perform a cryptographic handshake without ever transmitting your password. In /etc//ssh/sshDconfig, ensure password authentication is set to no and pubkey authentication is set to yes. Change default SSH port. Attackers often scan for SSH on its default port, 22. Changing it to a non-standard, high-numbered port e.g., 2222, 50,000 won't stop a determined attacker, but it will significantly reduce the noise from automated scans and opportunistic attacks. In etc//ssh/sshDconfig, change port 22 to your desired port number. Remember to update your firewall to allow traffic on this new port. Allow specific users only. If only a few users need SSH access, explicitly list them. In /etc//ssh/sshDconfig, add a line like allow users your username and other user. This is a strong security measure, denying access to any users not on that list. User privileges. Reinforce the principle of least privilege discussed in Chapter 7. Create separate standard user accounts for daily use. Grant sudo access only to users who absolutely need it for administrative tasks, and ensure they are part of the wheel group or a custom sudo group. Regularly review your user list and sudoers file to ensure no unnecessary accounts or privileges exist. Kernel hardening, sysctl. The Linux kernel itself can be tuned for security. While advanced kernel hardening can be complex, some basic sysctl parameters can improve security posture. Sysctl is a command that modifies kernel parameters at runtime. To make changes persistent, you place them in a file like etc//sysctld/99-sysctl.conf. Example parameters. netip4 tc_syncookies equals 1 helps protect against SYN flood attacks. netip4 IP forward equals 0 disables IP forwarding, preventing your system from acting as a router unless intended. Kernel sysig equals 0 disables the sysrq key, which can be useful for debugging but also abused. For most general-purpose systems, the default Arch kernel settings are reasonably secure, but for servers, these extra steps can add another layer of protection. 8.3 Firewall Configuration. Protecting network traffic. A firewall is your system's first line of defense against network-based attacks. It controls incoming and outgoing network traffic by enforcing network security policies. Think of it as a bouncer at the door, deciding who gets in and out. Arch Linux uses the NFtables framework by default, but for ease of use, we recommend a front-end like UFW, Uncomplicated Firewall. UFW, Uncomplicated Firewall. UFW is designed to be very easy to use while providing the full power of NFtables underneath. Installation. Type sudo pacman s-ufwa. Enable UFW. Type sudo ufwa enable. You will be warned that this might disrupt existing SSH connections. If you're connected remotely, ensure you allow SSH traffic before enabling, or you might get locked out. Default policies. By default, UFW sets excellent basic policies. Deny incoming. All incoming connections are denied by default. This is crucial for security. Allow outgoing. All outgoing connections are allowed by default, so your system can access the internet. Allowing specific services. You need to explicitly allow incoming connections for services you want others to access. To allow SSH, on the default port 22, sudo ufwa allow SSH. If you changed your SSH port, you'd specify the port. Sudo ufwa allow 2222/TCP. To allow web traffic, HTTP/HTTPS. Sudo ufwa allow HTTP, and sudo ufwa allow HTTPS. You can also specify port numbers directly. Sudo ufwa allow 80/TCP. For HTTP, sudo ufwa allow 443/TCP. For HTTPS. Denying specific rules. To block a specific IP address. Sudo ufwa deny from 192.168.1.100. To explicitly deny a service. Sudo ufwa deny telnet. Telnet is insecure and should never be used anyway. Checking status. Type sudo ufwa status verbose. This will show you which rules are active and whether UFW is enabled. Disable UFW. Type sudo ufwa disable temporarily disconnects the bouncer. NF tables for advanced users. NF tables is the modern replacement for iptables and is what UFW uses internally. It provides a more flexible and powerful syntax for defining firewall rules. For most users, UFW is sufficient, but if you have complex networking requirements or want very fine-grained control, learning NF tables is worthwhile. However, its configuration is outside the scope of an introductory chapter, and incorrect NF tables rules can easily lock you out of your server. 8.4 Intrusion detection and prevention. Beyond simply blocking unwanted traffic, you can deploy tools to detect and respond to malicious activities. Fail to ban. Fail to ban is a powerful server monitoring tool that scans log files for malicious activity, such as repetitive failed login attempts, brute force attacks. When it detects such activity, it automatically adds a rule to your firewall to temporarily or permanently ban the attacker's IP address. Installation. Type sudo pacman s failtoban. Configuration. Failtoban's main configuration is in etc failtoban jail.conf, but you should create a copy named jail local and make your edits there so they are not overwritten by updates. Open etc failtoban jail local in your editor. Ensure enabled equals true under the default section. Review the SSHD section. By default, it's often enabled or can be set to enabled equals true. This jail monitors SSH login attempts. You can adjust ban time, how long an IP is banned, find time window for failures, and max retrieve number of failures before ban. Enable and start service. Type sudo systemctl enable, now fail to ban service. Check status. Type sudo systemctl status fail to ban service. Type sudo fail to ban client status SSHD to see active bans for SSH. Fail to ban significantly reduces the noise from automated attack bots and protects your services, like SSH, FTP, web servers, from brute force attempts. Auditing and logging. Your system's logs are a treasure trove of information, including security-related events. Journoctl revisited. As discussed in Chapter 4, Journoctl is your primary tool for examining systems' unified journal. Regularly review logs for unusual activity, failed logins, or error messages. Journoctl U SSHD service. Review SSH daemon logs for suspicious login attempts. Journoctl PR. Look for error messages. You can filter further to find suspicious login attempts by looking for failed authentication messages specific to the SSH daemon. Audited, advanced. For highly critical systems, the Linux audit subsystem, managed by Audited, provides a much more detailed level of system call auditing. It can record every file access, process execution, and system call, which is invaluable for forensic analysis after a security incident. However, Audited requires careful configuration and can generate vast amounts of data, so it's usually reserved for specific compliance or high-security needs. 8.5 Software security and updates. Keeping your software up to date is a fundamental security practice. Importance of updates. Security vulnerabilities are discovered constantly. Software vendors and the Arch Linux community work diligently to patch these flaws. If you don't update your system, you remain vulnerable to known weaknesses. Arch Linux's rolling release model means that security patches are usually pushed to the repositories very quickly. This is a huge advantage over distributions with slower release cycles. Pacman CU revisited. Make sudo pacman CU a regular habit. Run it frequently, daily, or at least several times a week to ensure your system always has the latest security fixes, bug fixes, and performance improvements for all installed software from the official repositories. AUR security revisited. Review PKGBUILDs. As stressed in Chapter 3, always carefully review the PKGBUILD script before building and installing any package from the Arch user repository. Ensure it's not downloading source from suspicious locations or executing malicious commands. Remember, AUR packages are community submitted and not officially vetted by Arch developers. Never build as root. Always use makepkg as a regular user, not as root. This limits potential damage if a malicious pkgbuild contains exploit code. Trust your source. Only install AUR packages from trusted sources or maintainers, and prioritize packages with many votes and positive comments. Package signature verification. Pacman, by default, verifies the cryptographic signatures of all downloaded packages against the Arch Linux keyring. This ensures that the packages you download from the official repositories are authentic and have not been tampered with. Do not disable this feature. 8.6 Backup and recovery. Your last line of defense. No security measure is foolproof. Even the most hardened system can be compromised, suffer hardware failure, or fall victim to accidental data deletion. This is why a robust backup and recovery strategy is the absolute last and most critical line of defense. Security isn't just about preventing intrusion. It's also about ensuring data availability and system resilience in the face of disaster. Essential backup principles: regularity, backup frequently. The frequency depends on how often your data changes and how much data you can afford to lose. Redundancy, 3-2-1 rule, 3 copies. Keep at least 3 copies of your data, the original and 2 backups. 2 different media. Store backups on at least 2 different types of storage media, e.g., local hard drive and cloud storage. 1 offsite. Keep at least 1 copy offsite, away from your primary location, to protect against physical disasters like fire or theft. Testing. Crucially, regularly test your backups. A backup that cannot be restored is useless. Backup tools and strategies. rsync, a versatile command line utility for efficient incremental backups. It only copies changed files or parts of files, making it fast for subsequent backups. Great for local and remote synchronization. tar, for creating compressed archives of files and directories. Useful for full system snapshots or specific directory backups. Borgbackup or Ristic. Modern, secure, and efficient deduplicating backup programs. They provide strong encryption, compression, and allow for creating many backups while only storing unique data chunks once, saving space. Excellent for both local and remote encrypted backups. File system snapshots, BTRFS/LVM. As discussed in Chapter 5, if you use BTRFS or LVM, you can take near-instantaneous snapshots of your volumes. These are very useful for quick rollback before system updates, but they are not a substitute for full, off-site backups. Cloud storage. Solutions like Nextcloud, Syncthing, or commercial cloud providers can store off-site backups. 8.7 General security best practices. Keep services minimal. Only run services that are absolutely necessary. Every running service is a potential entry point for an attacker. Disable or uninstall services you don't use. Type sudo systemctl list unit files state equals enabled to see what services start at boot. Implement principle of least privilege for services. Configure services to run with the lowest possible user privileges. For example, a web server should not run as root. It typically runs as a dedicated user, e.g., HTTP. Understand what you install. Link back to the DIY philosophy. Carefully consider the source and necessity of every piece of software you add to your system, whether from Pacman or the AUR. Rootkit detection, chkrootkit, ArkHunter. While not foolproof, tools like chkrootkit and ArkHunter can help scan your system for signs of rootkits and other malicious software that might be hiding processes or files. Run them periodically. Type sudo pacman schrootkit ArkHunter. Type sudo chkrootkit. Type sudo ArkHunter check. Physical security. Don't forget physical security for servers. If an attacker has physical access to your machine, many software-based defenses can be bypassed. Stay informed. Follow security news, especially for Linux and for the software you run. Read the Arch Linux news before major updates. Case study snippet. A small company, proud of their self-hosted Arch Linux web server, found their website serving spam and ads one morning. Investigations revealed a series of failed SSH login attempts followed by a successful one around 3 a.m. The attacker, using a common password, quickly installed a small backdoor through a web-facing script, giving them persistent control. The company had mistakenly left the default SSH port open to the world, allowed password authentication, and crucially, hadn't enabled fail-to-ban. This single incident, stemming from a lack of basic hardening, cost them revenue, customer trust, and many hours of recovery. It was a stark reminder that even a minimal Arch install needs active security configuration from day one. Conclusion: securing your Arch Linux system is an ongoing journey that combines vigilance, informed decision-making, and consistent application of best practices. By embracing the Arch way of self-reliance and understanding the tools at your disposal, you can transform your minimal installation into a formidable fortress. From strong passwords and SSH hardening to robust firewalls and vigilant log monitoring, each step builds layers of defense. And remember, in the dire event that all other defenses fail, a comprehensive backup strategy is your ultimate safeguard. With your system now hopefully secure, the next chapter will focus on maintaining its health and performance over time. We'll explore system maintenance and optimization, ensuring your Arch Linux machine continues to run smoothly and efficiently long after its initial setup. Chapter 9: System Maintenance and Optimization, Keeping Arch Running Smoothly. Introduction. Congratulations! By now, you've not only mastered the installation of Arch Linux, but also gained proficiency in its core administration tasks like package management, service control, storage management, and vital security practices. Your Arch system is built, functional, connected, and reasonably secure. But a computer system, much like an engine, requires regular care and attention to maintain optimal performance, stability, and efficiency over time. It's not a set-it-and-forget-it affair. This ongoing care is the essence of system maintenance and optimization. For an Arch Linux administrator, this means more than just running software updates. It involves monitoring system health, managing disk space, fine-tuning performance, and executing routine checks to prevent small issues from escalating into major problems. Arch's rolling release model and minimalist nature mean that maintenance can be quite streamlined, but it still requires diligence and understanding. This chapter will guide you through the essential maintenance tasks and optimization techniques to keep your Arch Linux system running smoothly day in and day out. We'll cover routine updates, disk cleanup, performance monitoring, and other best practices that contribute to a healthy and efficient Arch installation for the long term. 9.1 Routine System Updates. The Arch Lifeline. As discussed in previous chapters, the rolling release model relies heavily on frequent updates. This isn't just about getting new features, it's primarily about security patches and bug fixes. Regularly updating your system is the single most important maintenance task. Why update regularly? Security. New vulnerabilities are discovered daily. Updates provide patches to these security holes, protecting your system from exploits. Stability and bug fixes. Updates fix bugs, improve software reliability, and resolve compatibility issues. New features and performance improvements. You'll gain access to the latest software versions and performance optimizations. Prevent partial updates. On a rolling release, doing very large, infrequent updates significantly increases the risk of conflicts and breakage, as packages might have interdependencies that change across many versions. Regular, smaller updates are less prone to issues. How to update: sudo pacman cu. The command for a full system update is simple: sudo pacman cu. As a reminder, S synchronizes package databases, Y downloads fresh copies of the master package databases, U upgrades all installed packages to their newest versions. Best practices for updates: run frequently, aim to run sudo pacman cu at least once a week, or even daily for critical systems and development environments. Read the news before a significant update, especially if it involves the kernel or core system components. Always check the official Arch Linux news page, archlinux.org/news, or its RSS feed. Developers post warnings about manual intervention required for cert updates or significant changes that might impact your system. Paying attention to these announcements can save you a lot of troubleshooting headaches. Handle warnings and errors promptly. If Pacman reports warnings, e.g., about configuration file changes, replace foo with bar, or errors, don't ignore them. Address them before proceeding or after the update completes. Resolve conflicts. Occasionally, Pacman might report package conflicts or dependency issues. Usually, it will offer to resolve them by removing or replacing conflicting packages. Carefully review the proposed actions before confirming. Restart services. After a kernel update, a reboot is required for the new kernel to take effect. For other critical system libraries, like systemd, glibc, it's often a good idea to reboot or at least restart affected services using systemtool. Checkupdates script, see below, can prompt you to update services which use new underlying versions of libraries. Helpful scripts, checkupdates and pacdiff. Checkupdates. You can install the Pacman contrib package to get the checkupdate script. Type sudo pacman s pacman contrib. Type checkupdates. This script safely checks for available updates without actually installing them or refreshing your local database. It's a great way to see what's pending before committing to a full update, especially on servers where you want to defer major changes. Pacdiff. Another useful script from Pacman contrib is pacdiff. When Pacman updates a package that includes a configuration file you might have modified, it saves your current version with a pacsave extension and installs the new version as filename pacnew. Pacdiff helps you find and merge these changes. Type sudo pacdiff. It will prompt you to compare your old configuration files with the new ones. It uses a tool like vimdiff or meld, if installed, to show you the differences, allowing you to merge changes and update your configuration files properly. This is crucial for avoiding breaking changes in services due to outdated configuration. 9.2 Disk Space Management. Keeping it lean. Over time, logs accumulate, package caches grow, and temporary files multiply. Efficient disk space management is crucial for performance and stability. Cleaning Pacman's cache. As discussed in Chapter 3, Pacman stores downloaded package files in /var/cache/pacman/pkg/. Remove unused package versions, sudo pacman sc. This command removes all cached packages that are no longer installed on your system and all but the newest versions of installed packages. It asks for confirmation. This is generally safe and recommended for routine cleanup. Remove all cached packages, use with extreme caution. Sudo pacman scc. This removes all packages from the cache, including those currently installed. While it frees up the most space, it means you cannot easily downgrade a package or reinstall an existing package without re-downloading it from the internet. Only use this if you are severely low on space and understand the implications. Removing orphan packages. When you install a package, Pacman automatically installs its dependencies. If you later remove that package, its dependencies might remain if no other installed package requires them. These are called orphaned or unneeded packages. List orphan packages. Pacman qtdq outputs only the names. Pacman qtd outputs name and version. Remove orphan packages. Sudo pacman rns, pacman qtdq. This command combines removal with the search for unneeded dependencies, ns. This is a safe and recommended cleanup operation. Clearing log files. System's journaled manages logs in var/log/journal/. While journaled is efficient, logs can still consume space, especially on busy servers. Check journal size. Journoctal disk usage. Clean journal by size, e.g., keep logs to 100 MB. Sudo journoctal vacuum size equals 100 M. Clean journal by time, e.g., keep logs for 7 days. Sudo journoctal vacuum time equals 7 days. Cleaning temporary files. Linux's /tmp directory is usually cleared on reboot, but large temporary files can accumulate if your system isn't frequently rebooted, e.g., servers. Old downloads and unpacked archives. Check your user's downloads folder, /, cache directory, and any temporary build directories, e.g., from AUR manual builds for old files. Remember, some AUR helpers like yay have their own cache which can be cleaned with commands like yay, scc. This is specific to the helper, not Pacman directly. 9.3 Monitoring system health. Staying ahead of problems. Proactive monitoring allows you to detect potential issues before they become critical. CPU, memory, and load. HTOP, an interactive real-time process monitor. Install with sudo pacman s htop. It provides a colorful and easy-to-read overview of CPU usage, memory usage, swap usage, and a list of running processes sorted by resource consumption. Top, the classic command line process monitor, usually pre-installed. A bit less user-friendly than HTOP, but provides similar information. Free H reports memory and swap usage in a human-readable format. Uptime shows how long the system has been running, the number of logged-in users, and the system load averages, a measure of CPU demand over time. Disk I/O. IOTOP shows current disk I/O activity by process. Install with sudo pacman s IOTOP. Useful for identifying which processes are heavily reading from or writing to disk. IOSTAT reports CPU utilization and disk I/O statistics, part of systat package. Network activity. SS command to investigate sockets, like netstat but more modern. Use SS tulpan to show listening TCP UDP ports, SSS for summary statistics. Nload, simple command line tool for monitoring network traffic and bandwidth usage. Install with sudo pacman s nload. Temperature, for physical machines, especially laptops or self-built PCs, monitoring CPU and GPU temperatures is important to prevent overheating and identify potential cooling issues. LM Sensors, a package that provides command line tools to monitor hardware sensors, temperatures, voltages, fan speeds. Type, sudo pacman slm sensors. Type, sudo sensors detect, follow prompts to set it up. Type, sensors to view readings. 9.4 System optimization, fine-tuning performance. While Arch is inherently lean, a few optimizations can further improve performance and resource usage. Services management, systemed. The less, the better. As a rule of thumb, disable any systemed service you don't actively use. Each running service consumes resources, CPU, RAM, and potentially opens a security vulnerability. List all enabled services. Systemtl list unit files, type equals service state equals enabled. Disable an unused service. Sudo systemtl disable service name service. Stop a running service. Sudo systemtl stop service name service. Swappiness, managing swap usage. Swappiness is a kernel parameter that controls how aggressively your Linux system uses swap space. Values range from 0 to 100. Swappiness equals 0. The system will use swap only when absolutely necessary, when RAM is almost full. This is generally good for desktop users with plenty of RAM, as it favors keeping data in faster RAM. Swappiness equals 60, default, a balanced approach typical for servers where some swapping is acceptable. Swappiness equals 100. The system will favor moving processes to swap more readily to free up RAM. This might be suitable for systems with very limited RAM or specific workloads that benefit from consistent disk cache. To check current swappiness, cat/proc/sys/vm/swappiness. To change it temporarily, until reboot, sudo systl vm swappiness equals 10. To make it permanent, add vm swappiness equals 10 to a systl configuration file, like /etc//d/99-systl.conf. SSD optimization trim. If you have an SSD, enabling trim can improve its performance and longevity by allowing the operating system to inform the SSD which data blocks are no longer in use and can be erased internally. Check if trim is enabled on boot. Add the discard option to your SSD's fstab entry, defaults no time discard. This performs trim operations instantly upon file deletion. Be aware that some debate exists on whether discard affects performance. Some prefer periodic trim. Periodic trim, recommended for many users. fstrim timer is a system timer unit that runs fstrim service weekly by default. fstrim performs a trim operation on all mounted file systems that support it, helping keep your SSD optimized. To check if it's enabled, systemtl status fstrim timer. Enable it if it's not. Sudo systemtl enable, now fstrim timer. Customizing boot services and daemons. While systemtl disable is powerful, for very specific performance tuning, you can also modify some systemed service files, especially those you create. However, this is advanced and should be done cautiously. The systemdanalyze command can help you understand your boot process and identify bottlenecks. Systemdanalyze blame shows which services are taking the longest to start during boot. Systemdanalyze plot boot SVG generates an SVG image of the boot process timeline. 9.5 Regular system checks and housekeeping. Check for failed system services. Systemtool failed. Regularly check this to see if any services failed to start or stopped unexpectedly. Investigate logs, journaltool use service name for failed services. File system checks. While mostly automatic at boot, understanding FSCK Chapter 5 is important for manual troubleshooting if issues arise. Kernel log demyst show with human-readable timestamps. Review the kernel ring buffer for hardware errors, driver issues, or other low-level problems that might not show up in regular system logs. Review SMART data. For hard drives and SSDs, SMART, self-monitoring, analysis and reporting technology, can provide early warnings of impending drive failure. Install SmartMon tools. Sudo Pacman as SmartMon tools. Check drive health. Sudo smarttool h dev/sda, replace dev/sda with your drive. Run self-tests. Sudo smarttool t short dev/sda or long. Anecdote: I once inherited an Arch Linux server that was sluggish and would occasionally freeze. Logging in revealed very high CPU usage and nearly full RAM, but no obvious applications consuming resources. Digging into Systemtool, failed showed several obscure, non-critical services constantly crashing and restarting. Each crash generated a large core dump, filling the disk, and each restart consumed a burst of CPU and RAM. Disabling these unnecessary, broken services, coupled with a Pacman SC to clean the now massive cache, instantly brought the server back to life. This experience underscored that sometimes, optimization isn't about more power, but less unnecessary work, and that even small, failed services can collectively create huge performance headaches if ignored. Conclusion: system maintenance and optimization are not merely chores, but critical components of a healthy and resilient Arch Linux environment. By diligently performing routine updates, managing disk space, proactively monitoring system health, and applying sensible optimizations, you ensure your system remains stable, performs optimally, and is less prone to unexpected failures. This ongoing commitment to care transforms your Arch installation into a reliable workhorse, ready for any task you throw at it. However, even with the best maintenance, things can occasionally go wrong. In the next chapter, we will shift our focus to troubleshooting common issues, providing you with strategies and tools to diagnose and resolve problems that inevitably arise in any complex computing system. Chapter 10. Troubleshooting common issues, diagnosing and fixing problems. Introduction. No matter how diligently you follow best practices for installation, configuration, and maintenance, every system administrator eventually encounters problems. Linux, including Arch Linux, is incredibly robust, but software bugs, hardware failures, misconfigurations, and human error can all lead to unexpected behavior. The ability to effectively diagnose and troubleshoot these issues is one of the most valuable skills for any administrator. It transforms a frustrating roadblock into an opportunity to deepen your understanding of the system. Arch Linux, with its transparent design and exceptional documentation, provides a fertile ground for learning troubleshooting. However, its minimalist approach means you're often working at the command line, requiring a systematic approach and an understanding of the right tools to use. This chapter aims to equip you with that mindset and toolkit. We'll outline a general troubleshooting methodology, cover common Arch-specific problems, and provide practical commands and strategies for diagnosing and resolving them. 10.1 A general troubleshooting methodology, the scientific approach. Effective troubleshooting isn't just about knowing commands, it's about following a logical process. Think of yourself as a detective, gathering clues and testing hypotheses. Identify the problem, what exactly is happening. E.g., web server is not responding, can't connect to Wi-Fi, system won't boot. What are the symptoms? E.g., error message X appears, no network connection, screen is black. When did it start happening? Was anything changed recently? E.g., after a system update, after installing a new package, after editing a configuration file. This is often the most important clue. Gather information, check relevant logs, system journal, application logs, verify service status. Check resource usage CPU, RAM, disk space. Confirm configuration file contents. Use status commands for network, disk, etc. Formulate a hypothesis. Based on the information, what do you think is causing the problem? E.g., the web server service isn't running, the network interface is down, a recent update broke a dependency. Test the hypothesis. Try a small, isolated change or command that would confirm or deny your hypothesis. E.g., try restarting the web server, manually bring up the network interface. Try downgrading the problematic package. Be cautious, make only one change at a time, and consider the potential impact. Evaluate the results. Did the change fix the problem? If yes, great. Document the solution. If no, did it give you new information? Refine your hypothesis and go back to step 3. Document the solution and the process. Even if you fix it, learning comes from understanding why it happened and how you fixed it. This will save you time if you, or someone else, encounter the same issue again. Crucial advice: check the Arch Wiki first. For Arch Linux, the official Arch Wiki, wiki.archlinux.org, is your primary troubleshooting resource. Most common issues are well documented there, often with solutions. Before searching general Linux forums, always check the Arch Wiki for your specific problem. It's kept up to date with Arch's rolling release. 10.2 Common boot issues. A system that won't boot is one of the most frustrating problems. Problem: system doesn't boot, stuck at a black screen or grub prompt. Possible causes and troubleshooting. Improper grub configuration installation. This is common after a fresh install or a major kernel update if grub mkconfig wasn't run. Troubleshooting. Boot from Arch Live USB. Your Arch installation media is your best friend for recovery. Mount your system. Sudo mount /dev/sdax/mnt, where dev/sdax is your root partition. If you have other partitions, e.g., /boot/EFI, mount them too. Archroot. Sudo archroot/mnt. Reinstall grub UEFI. Grub install target equals x8664 EFI directory equals /boot/EFI bootloader ID equals grub. Reinstall grub BIOS. Grub install dev/sda, replace SDA with your disk, not partition. Regenerate grub config. Grub mkconfig o/boot/grub/grubcfg. Exit croot umount r/mnt, then reboot. Corrupted kernel or initramps. Troubleshooting. From the grub menu, try booting an older kernel version, if available in the Advanced Options for Arch Linux menu. If an older kernel boots, try reinstalling the latest Linux package and Linux firmware within your crooted environment, then regenerate grub. Pacman s Linux firmware. Then rerun grub mkconfig as above. Kernel panic. Kernel panic messages indicate a critical, unrecoverable error in the kernel. This can be due to hardware issues, corrupted kernel files, or incompatible drivers. Troubleshooting. Read the message. It often points to a specific driver or module. Boot with an older kernel if possible. Check your hardware. Reinstalling Linux and Linux firmware is a good first step. fstab errors. An incorrect entry in etc/fstab can prevent your system from booting, often resulting in a message that you are dropped to a maintenance shell or emergency mode. Troubleshooting. Look for the error message. It usually names the problematic device or mount point. Mount root, read-only. In the emergency shell, you might be able to mount your root partition mount o remount, RW, and then edit etc/fstab to fix the error. Boot from live USB. Mount your root partition from the live environment, then edit /mnt/etc/fstab to comment out or correct the problematic line. 10.3 Post-update issues. A common scenario on rolling release distros is a problem occurring immediately after sudo pacman su. Problem: application or system functionality is broken after update. Possible causes and troubleshooting. Manual intervention required. You didn't read the Arch Linux news. Some updates require manual steps, e.g., merging, Pacman files, changing a service name, re-enabling a module. Troubleshooting, check archlinux.org/news for recent announcements. Look for manual intervention is required or important changes. Use Pactif to find and merge Pacman configuration files. Bug in recent update. Occasionally, a bug might slip into a new package version. Troubleshooting, check Arch Linux forums IRC channels, see if other users are reporting the same issue. Downgrade the problematic package. If you can identify the package, and its previous version is still in your Pacman cache, /var/cache/pacman/pkg/, you can downgrade it. Sudo pacman uvar/cache/pacman/pkg/ package name old version pkg tarzisti. If not in cache, you can find older packages on the Arch Linux archive or in Arch Mirror. Be cautious with downgrades as they can introduce dependency issues. Report the bug. Once confirmed, report the bug on the Arch Linux bug tracker. Configuration file overwrite. An update might overwrite a configuration file you customized. Troubleshooting, always check for Pacman files using Pactif or by searching for find etc. name, Pacman. Merge changes appropriately. 10.4 Network connectivity issues. We covered network configuration in Chapter 6. Here's a quick recap of troubleshooting steps. Problem: no internet connection or cannot reach certain network resources. Troubleshooting: is the interface up and running? IP. If not, use sudo IP link set dev interface name up. Does it have an IP address? IP. If using DHCP, check your DHCP client's status, e.g., systemtool status DHCP-CD or journoctal U network manager. If static, double-check your configuration file, etc. system network or nmcli connection show. Is the default gateway set correctly? IPR. Check journoctal U network manager or journoctal U system networked for related errors. Can you ping your default gateway? Ping gateway up. If not, problem is local or on the router switch. Check cables, Wi-Fi signal. Can you ping an external IP address, e.g., 8.8.8.8? Ping 8.8.8.8. If yes, but cannot ping domain names, google.com, then you have a DNS issue. DNS troubleshooting. Check resolvectal status to see configured DNS servers. Check /etc/resolve.conf, though often managed by Systemd Resolved or Network Manager. Try nslookup google.com or dig google.com. Firewall. Is your firewall, UFW or NF tables blocking traffic? Sudo ufwa status. Temporarily disable, sudo ufwa disable. To rule it out, re-enable immediately. 10.5 Service failures. When a service isn't starting, behaving incorrectly, or crashing. Problem: a service is not running or behaving as expected. Troubleshooting commands, check service status. This is your primary diagnostic tool. Systemtool status service name service. Look for active, failed or active, inactive. Pay close attention to error messages in the output, especially main PID, memory, and the lines below process, and C group, and the last few lines of log output. Examine logs with journoctal. Dive deeper into the service's logs. Journoctal U service name service no pager removes paging for easier scrolling through all logs related to the service. Look for error, failed, critical, or other obvious indicators. If it's a web server, check its own access and error logs, e.g., /var/log/apache2/error log or var/log/nginx/error log. Check configuration files. Misconfigurations are a common cause of service failures. Carefully review the service's main configuration file, often in /etc/service name/. Look for Pacman files if it's an update-related issue using Pactif. Check permission issues on config files or data directories. Resource exhaustion. Is the system out of memory? Free H. Out of disk space? DFH. CPU overloaded? HTOP. Try restarting reloading. Sudo systemtool restart, service name service. Sudo systemtool reload service name service, if it supports it. Dependency issues. Sometimes a service fails because a dependency isn't met. Systemtool status usually indicates this. Ensure dependencies are enabled and running. 10.6 Frozen or unresponsive system. Problem: the system is completely unresponsive, no keyboard input, mouse frozen. Troubleshooting. check for disk activity. Is the disk LED constantly on? The system might be thrashing, swapping excessively to disk. Magic sysRQ key. This allows you to perform low-level kernel commands even on a frozen system. It's often disabled for security reasons, so you might need to enable it. Sudo sysctl kernel sysic equals 1. Hold Alt plus sysRQ, often print screen, and then type the sequence, REISUB slowly. R. Unraw, take control of keyboard. E. Terminate, send SIGTRM to all processes. I. Kill, send SIGKILL to all processes. S. Sync all mounted file systems. U. Unmount, remount all file systems read-only. B. Reboot the system immediately. This is a last resort to safely reboot an otherwise unresponsive system, saving your data from corruption. Hard reset. If REISUB fails, a hard reset, holding down the power button until it shuts off, is your only option, but it carries a higher risk of data corruption. Afterward, let FSCK run at boot. 10.7 General Tips and Tools. Dmesc, check kernel messages for hardware errors, dmesc-t. lsusp, lspci. List connected USB devices and PCI devices to verify hardware detection. lsblk-f, show block devices, partitions, file system types, and UIDs. Crucial for disk and fstab related issues. Read error messages. Linux error messages can be intimidating, but they often contain very specific clues. Read them carefully. Search for them online. Isolate the problem. Try to narrow down the problem. Is it network-wide or just one device? Does it affect all users or just one? Does it happen with all applications or just one? Reboot, often but not always. A reboot can sometimes clear transient issues, but it should be a last resort after attempts at diagnosis, not a primary troubleshooting step. If it fixes the problem, you often haven't learned why it happened. Community support. If you're truly stuck, the Arch Linux forums are a great place to ask for help. Provide detailed information, your troubleshooting steps, log outputs, and exact error messages. Anecdote. One of my earliest Arch troubleshooting experiences involved my desktop randomly freezing. It was intermittent, making it incredibly hard to diagnose. I checked logs, processes, network, everything I knew. Finally, I decided to check dmesc and noticed a cryptic error message about firmware and my Wi-Fi card. It turned out a recent Linux firmware update had a regression with my specific model of Wi-Fi adapter. Downgrading just that one firmware package from my Pacman cache instantly resolved the issue. This taught me that troubleshooting is often about persistence and knowing where to look, even in the system's most obscure corners. Conclusion. Troubleshooting is an art as much as a science. It demands patience, meticulous observation, and a systematic approach. By embracing the general methodology, familiarizing yourself with Arch-specific tools like systemctl and journoctl, and leveraging the invaluable ArchWiki, you can confidently tackle most problems that arise on your Arch Linux system. Every issue you diagnose and resolve deepens your understanding and makes you a more capable system administrator. Having equipped you with the skills to troubleshoot, we will now explore ways to automate tasks and streamline your administrative workflow. In the next chapter, Automation and Scripting, we will delve into the world of shell scripting and scheduling, turning repetitive manual tasks into efficient, automated processes. Chapter 11, Automation and Scripting, Streamlining Administration Tasks. Introduction. By now, you've gained a comprehensive understanding of Arch Linux, from its philosophical underpinnings and installation to managing packages, services, security, and even troubleshooting. As you become more proficient, you'll notice that many administrative tasks are repetitive. Updating systems, cleaning caches, checking logs, monitoring various metrics, or deploying applications. Performing these manually for one system is manageable, but imagine doing it for dozens or hundreds of servers. This is where automation and scripting become indispensable. Automation is about using tools and scripts to perform tasks without direct human intervention, reducing human error, saving time, ensuring consistency, and freeing administrators to focus on more complex, strategic problems. On Linux, the shell is your primary interface, and shell scripting is the most fundamental form of automation. Coupled with job schedulers like cron or system timers, you can create powerful, self-executing routines. This chapter will introduce you to the core concepts of shell scripting and provide practical examples relevant to Arch Linux administration. We'll explore how to write basic scripts, manage variables, use conditional logic, and then show you how to schedule these scripts to run automatically. Mastering these skills will significantly streamline your workflow and transform you into a more efficient system administrator. 11.1 The Power of the Shell and Basic Scripting. The Linux shell, most commonly Bash on Arch Linux, is not just for typing commands one by one. It's a powerful programming environment. A shell script is simply a sequence of shell commands stored in a file, which the shell then executes line by line. Why script? Automation. Automate repetitive tasks or sequences of commands. Consistency. Ensure tasks are performed identically every time. Efficiency. Execute complex tasks rapidly. Error reduction. Minimize human typing errors. Documentation. A script serves as documentation of the steps required to perform a task. Your first script, a system update and cleanup. Let's create a simple script to perform a full system update and clean the Pacman cache. Create the script file, type nano maintenance script sh. The sh extension is conventional for shell scripts, though not strictly required. Add the script content, bin bash. Hash. This script performs a full Arch Linux system update and cleans the Pacman cache. Echo, starting Arch Linux system update. Sudo pacman su not confirm. If x0, then echo system update completed successfully. Now cleaning old packages from Pacman cache. Sudo pacman sc not confirm. Echo Pacman cache cleaned. Echo checking for orphan packages and removing them. Sudo pacman rns pacman qtdq not confirm. Echo orphan packages removed. Else echo system update failed. Please check for errors. Phi echo maintenance script finished. Bin bash. This is called the shebang line. It tells the system which interpreter to use for running the script, in this case bash. It must be the very first line. Hash this script. Lines starting with hash are comments. They are ignored by the shell and are for human readability. Echo prints text to the terminal. Sudo pacman su not confirm performs the update. Not confirm is usually avoided in interactive scripts for safety, but for fully automated maintenance, it might be desirable. Use with caution. If x0, then phi. This is a basic conditional statement. $, contains the exit status of the last executed command. An exit status of 0 typically means the command succeeded, and anything else indicates an error. Sudo pacman sc not confirm cleans the Pacman cache. Sudo pacman rns pacman qtdq not confirm removes orphan packages. Performs command substitution, running pacman qtdq and using its output as arguments to sudo pacman rns. Make it executable. Type chmod plus x maintenance script sh. This provides execute permission to the script. Run the script. Type maintenance script sh. Scripting building blocks. Variables. Store data in memory. Name equals John Doe. File path equals /var/log/myaplog. Access with echo hello name. Input output. Read p enter your name. Username. Prompts for user input and stores it in the username variable. Conditional statements if, elif, else. Execute code based on conditions. If filepath, then echo file exists. Elif d filepath, then echo it's a directory. Else echo file or directory does not exist. Phi common conditions. F is a regular file, D is a directory, Z string is empty, N string is not empty, EC equal to, Ni not equal to, GT greater than, LT less than. Loops for while, repeat a block of code. Hash iterate over a list of users. For user and user 1, user 2, user 3. Do. Echo processing user, user. Hash commands to execute for each user. Done. Hash loop until a condition is met. Count equals 0. While count LT5. Do. Echo count count. Count equals $, count plus 1, hash increment count. Sleep 1 hash wait 1 second. Done. Functions, organize code into reusable blocks. Log message. Echo $date plus %y%m%d%h %m%s. $1/var/log/miscript log. Log message, script started successfully. Command substitution. Execute a command and replace it with its output. Current date equals $date plus %y%m%d. Redirection, control where command output goes. Command file. Redirects standard output to file, overwriting file. Command file, redirects standard output to file, appending to file. Command to error file, redirects standard error to error file. Command and file. Redirects both standard output and standard error to file. Scripting best practices. Start simple, don't try to automate too much at once. Build scripts incrementally. Test thoroughly. Test scripts in a safe environment before running them on production systems, especially those with knock-confirm or RM commands. Use full paths. Avoid relying on the path environment variable. Use /usr/bin/pacman instead of pacman to avoid ambiguity. Error handling. Use set E at the beginning of your script. This causes the script to exit immediately if any command fails, returns a non-zero exit status. Logging. Output important messages to a log file, /var/log/miscript log, in addition to or instead of the screen. Comments. Explain complex parts of your script for future reference. Version control. Store your scripts in a version control system like Git. 11.2 Scheduling tasks, cron and system timers. Once you have a script, you need a way to run it automatically at specific times or intervals. Linux provides several powerful tools for this. Cron, the traditional job scheduler. Cron is the classic Unix Linux utility for scheduling commands or scripts to run periodically. Cron jobs are defined in a special format called a crontab, cron table. System-wide crontab, etc/crontab and files in /etc/crond/ are for system-wide tasks. User-specific crontab. Each user can have their own crontab, which is edited with the crontab E command. It runs commands with that user's permissions, which is safer for most administrative tasks than running everything as root. You should add your script to the root crontab if it uses sudo inside. Crontab syntax. A crontab entry has 5 time fields followed by the command to execute. Minute, hour, day of month, day of week, command to execute. Minute, 0 to 59. Hour, 0 to 23. Day of month, 1 to 31. Month, 1 to 12, or JANDC. Day of week, 0 to 7, 0 or 7 is Sunday, 1 is Monday. Wildcard matches all values. Separator for lists, e.g., 115 for the 1st and 15th. Range, e.g., 9 to 17 for 9 a.m. to 5 p.m. Slash, step values, e.g., 15 for every 15 minutes. Example crontab entries. Run a script every day at 3 o'clock a.m. 03/home/user/maintenance-script/sh for users crontab. 03 root home/user/maintenance-script/sh. For system-wide crontab, explicitly specify user. Run a command every Monday morning at 5:30 a.m. 35:1/usr/bin/sumbackup command. Special strings. Cron also supports several convenient aliases. At reboot, at yearly, at monthly, at weekly, at daily, at hourly. To run on reboot. At reboot home/user/startup script/sh. Editing crontab for your own user's crontab. Crontab E, first time you might be asked to choose an editor, pick Nano. For roots crontab. Sudo crontab E. List existing crons, crontab L. Cron best practices, environment, cron environments are minimal. Scripts should use full paths /usr/bin/pacman as opposed to pacman. Output. Redirect output to a log file, miscript/sh var/log/miscript cronlog2 and 1 to capture both standard output and errors, as cron jobs usually don't have a terminal attached. Testing. Always test your cron jobs by running them manually first. System timers, the modern scheduler. System timers, timer units, are system's native way to schedule tasks. They are more flexible and robust than cron and integrate seamlessly with systems' logging capabilities. They are composed of 2 parts: a service unit, the task to run, and a timer unit, when to run it. Advantages of system timers over cron. Better logging. Output goes directly into the system journal, making it easier to monitor and debug with journoctl. Dependency management can be configured to run only after specific services are up or certain conditions are met. Event-based scheduling can be triggered by events, e.g., after boot, after network is up, not just fixed times. Robustness. If the system is off during a scheduled time, the job can be configured to run as soon as the system is back online. Example: scheduling a daily maintenance script with system timers. Create a service unit file. This defines what command to run. Type: sudo nano, etc. system arch maintenance service. Unit. Description equals daily Arch Linux maintenance. Service. Type equals one-shot. Exec start equals /home/user/maintenance script sh. Hash you might want to unset these if your script already handles logging and error checks. Standard output equals journal. Standard error equals journal. User equals user hash or root. If your script uses sudo internally. Type equals one-shot. The service runs a single command and then exits. Exec start. The command to execute. Use the full path to your script. User specifies which user the script runs as. This is important for permissions. Create a timer unit file. This defines when the service should run. Type: sudo nano etc. system arch maintenance timer. Unit. Description equals run daily Arch Linux maintenance script. Timer. On calendar equals daily. Hash or for a specific time. On calendar equals 300. Hash or to run 15 minutes after boot. On boot sec equals 15 min. Hash or if missed, run immediately after boot. Persistent equals true. Install. Wanted by equals timer's target. On calendar defines the schedule. Daily is simple. 300 means every day at 3 a.m. Persistent equals true. If the system is off when the timer is due, it will run the service shortly after boot. Wanted by equals timer's target ensures the timer is activated when the timer system starts. Enable and start the timer. Type: sudo systemctl daemon reload to load the new unit files. Type: sudo systemctl enable now arch maintenance timer. Enable and start the timer. Note that you enable the timer unit, which in turn activates the service unit. Check status and logs. Type: systemctl status arch maintenance timer. Type: journoctl u arch maintenance service to see the service output. Type: journoctl u arch maintenance timer to see the timer's logs. System timers offer a powerful and integrated approach to scheduling tasks, making them the preferred choice for more complex or critical automated tasks on an Arch Linux system. Anecdote: early in my career, running manual system updates on a dozen Linux servers became a nightmare. One server was always missed, or a config pacman would be forgot. I wrote my first simple bash script to automate Pacman, CU, and pacdiff merging. Then I configured it with cron. Suddenly, a multi-hour chore became a single command that ran automatically. More importantly, it ensured consistency. This small script not only saved me immense time, but also prevented future headaches. It was a tangible example of how even basic automation can dramatically improve efficiency and reliability in system administration. Conclusion: automation and scripting are not just for experienced developers. They are essential skills for any modern system administrator. By leveraging the power of shell scripting, you can transform repetitive, manual tasks into efficient, consistent, and error-free automated processes. Combined with job schedulers like cron or the more advanced system timers, you can ensure that your Arch Linux system performs essential maintenance, monitoring, and administrative routines without direct human intervention. This shift from manual execution to automation will not only save you valuable time, but also foster a more reliable and self-managing system, freeing you to tackle larger, more strategic challenges. In our final chapter, Beyond the Basics, we'll explore avenues for continued learning and delve into more advanced topics and resources, guiding you on your ongoing journey as an Arch Linux administrator. Chapter 12. Beyond the Basics, Exploring Further. Introduction. Congratulations! You've reached the final chapter of this handbook, having journeyed from the philosophical foundations of Arch Linux through its hands-on installation, core administrative tasks, essential security measures, and the power of automation. You now possess a strong practical understanding of how to build, manage, troubleshoot, and maintain a robust Arch Linux system. This foundation is invaluable, not just for Arch, but for any Linux distribution you may encounter in your system administration career. However, the world of Linux is vast and ever-evolving. This book serves as a starting point, a comprehensive introduction to the essentials. True mastery comes from continuous learning, experimentation, and diving deeper into specialized areas. Arch Linux, by its very nature, encourages this relentless pursuit of knowledge, offering you a direct pathway to explore advanced concepts and technologies. In this concluding chapter, we will look beyond the basic toolkit you've acquired. We'll suggest advanced topics for your continued exploration, highlight valuable resources, and encourage the mindset of lifelong learning that defines a proficient system administrator. Your journey with Arch Linux and the broader Linux ecosystem has just begun. 12.1 Advanced Topics to Explore. The skills you've developed are transferable. Here are some exciting and valuable areas to explore next, pushing your administrative capabilities further. Virtualization and containers. The ability to run multiple isolated operating systems or applications on a single physical machine is fundamental in modern IT. Virtual machines, VMS. Explore KVM, kernel-based virtual machine, and QEMU for full virtualization. Tools like VirtManager provide a graphical interface for managing VMs. Understanding VMS is crucial for setting up development environments, testing new configurations, or deploying multiple server roles. Containers. Containers, like Docker and Pacman, offer a lightweight alternative to VMS, providing process isolation and enabling consistent application deployment. Learn how to build, run, and manage containerized applications, as they are rapidly becoming the standard for modern software deployment. Advanced file systems. While ext4 is robust, delve deeper into file systems that offer more advanced features. BTRFS, B-tree file system. Revisit BTRFS as discussed briefly in Chapter 5. Master its snapshot capabilities for easy system rollbacks, understand subvolumes for flexible partitioning, and explore its built-in RAID and data integrity features. ZFS, Zettabyte file system. A powerful, enterprise-grade file system known for its strong data integrity features, snapshots, volume management, and impressive performance for large datasets. While not native to the Linux kernel, it's widely used in server environments. Network services and infrastructure. From simple web servers to complex network infrastructures, Linux is the backbone. Expand your knowledge by setting up and managing web servers. Go beyond basic configuration. Master advanced features of Apache, HTTPD, and Nginx, including virtual hosts, reverse proxies, and performance tuning. Database servers. Install and manage robust databases like PostgreSQL and MariaDB, MySQL. Understand their configuration, backup strategies, and basic performance optimization. Mail servers. While complex, setting up a secure mail server, e.g., Postfix, Dovecot, is an ultimate test of your Linux networking and security skills. File sharing. Delve into advanced Samba configurations for Windows interoperability or NFS for Linux-Unix networks. VPNs, virtual private networks. Understand how to set up and manage secure VPN solutions, e.g., WireGuard, OpenVPN, to create encrypted tunnels for remote access or secure site-to-site communication. Configuration management. As your number of systems grows, manual configuration becomes unsustainable. Configuration management tools automate the deployment, configuration, and orchestration of entire fleets of servers. Ansible, a popular agentless, meaning it doesn't require software running on target machines, automation engine that uses simple YAML-based playbooks to define system states. It's often recommended for beginners in configuration management due to its low learning curve. Puppet and Chef, more complex client-server models that offer powerful capabilities for large-scale infrastructure automation. Monitoring and alerting. Beyond basic command-line tools like htop, establish comprehensive monitoring solutions. Prometheus and Grafana, a popular open-source stack for collecting metrics, Prometheus, and visualizing them with beautiful dashboards, Grafana. Nagios/Zabbix, traditional monitoring systems for checking service availability and performance capable of sending alerts. Elk Stack, Elasticsearch, Logstash, Kibana. A powerful suite for centralized log management, enabling you to collect huge volumes of log data, search them efficiently, and create interactive dashboards for analysis and alerting. Advanced Security. Build on the security foundations from Chapter 8. Mandatory Access Control Mac. Explore SE Linux or AppArmor, which provide fine-grained control over what processes can access what resources, adding another layer of security beyond traditional Linux permissions. Vulnerability Scanning. Learn to use tools like Nessus or OpenVAS to identify potential security weaknesses in your systems. Intrusion Detection Systems, IDs/Intrusion Prevention Systems, IPS. Understand how to use tools like Snort or Suricata to detect and potentially block malicious network traffic patterns. Kernel Compilation and Customization. For very specific hardware or performance needs, you might compile your own Linux kernel, optimizing it for your exact system or adding experimental features. Arch Linux's PKGBUILD system makes this process manageable, even for custom kernels. Custom kernels. Learn how to create PKGBUILDs to compile the latest Linux kernel from scratch, optimizing for specific hardware or disabling rarely used features. 12.2. Honing your skills and resources. Your journey as a proficient Arch Linux administrator is a marathon, not a sprint. Here's how to keep learning and improving. The Arch Wiki, your constant companion. This book emphasizes the Arch Wiki, and for good reason. It is arguably the best single source of Linux documentation available. It's comprehensive, accurate, always up to date, and written for users who want to understand how things work. Make it your first stop for any question or problem. Official documentation, man pages, and info. Don't underestimate the power of man pages. For every command you use, e.g. man Pacman, man systemtool, there's a detailed manual page. Info pages, info corutils, offer a more tutorial-like explanation for some core utilities. Experimentation in controlled environments. Set up virtual machines using KVM or VirtualBox to experiment freely. Break things, fix them, and learn from the process without fear of damaging your production system. Use snapshots to quickly revert to a known good state. This is perhaps the most effective way to learn. Active community engagement. Arch Linux forums. The official Arch forums, bbs.archlinux.org, are a great place to ask questions, share knowledge, and learn from experienced users. Remember to search first and provide detailed information when asking for help. IRC channels. Join relevant IRC channels, e.g. Arch Linux on LiberaChat. Mailing lists. Subscribe to specialized mailing lists for specific services or technologies you're interested in. Learn a programming language. While shell scripting is powerful, learning a general-purpose programming language like Python, often considered the de facto language for system administration and automation, Perl or Ruby, will dramatically expand your capabilities for writing more complex and sophisticated automation scripts and tools. Contribute to open source. Get involved in open source projects. This could mean contributing to the Arch Wiki, reporting bugs, helping other users, or even contributing code. It's an excellent way to learn, collaborate, and give back to the community. Hands-on projects. Build personal projects. Set up a home server, host a website, configure a media server, or automate your backups. Practical application of knowledge solidifies your understanding. Linux certifications. Consider pursuing professional Linux certifications, e.g., Linux Professional Institute, LPI certifications like LPIC-1, LPIC-2, Red Hat Certified System Administrator, RHCSA, CompTIA Linux Plus. While experience is paramount, certifications can validate your skills and demonstrate your knowledge to potential employers. Stay curious. The most important trait of a great administrator is curiosity. Always ask, how does this work? And what if I try this? The Linux ecosystem is a vast territory for endless discovery. The journey continues. You started this book with a step-by-step plan to learn Arch Linux system administration, and you've systematically worked through it. You've embraced the do-it-yourself philosophy and gained a deep appreciation for Arch's elegant simplicity and powerful control. This control, however, is a double-edged sword. With great power comes great responsibility. You are now equipped with the tools and knowledge to wield that power responsibly, to build and manage systems that are not just functional, but also robust, secure, and efficient. Remember, Arch Linux is not just an operating system, it's a commitment to learning. It actively encourages you to understand the underlying mechanics of your system, making you a more knowledgeable and capable administrator on any Linux platform. The skills you've developed are the foundation for a lifelong journey of exploration in the dynamic world of computing. Embrace the challenge, enjoy the process of discovery, and continue to build, tinker, and explore. The Arch Linux community and the broader open-source world await your continued contributions. Good luck and happy administering!